In 1972, NASA test-fired a nuclear engine in the Nevada desert that produced more thrust per kilogram of propellant than any chemical rocket ever built. It was called NERVA. Within the decade, Congress shut the program down, the test rig was disassembled, and the engineers who built it went home. We have never tested another nuclear rocket on American soil. Welcome to Space Cluster, where we trace the engineering the space age tried to forget. The rockets, America buried. The reactors that worked. The programs that died in filing cabinets, in committee rooms, in budget cuts approved by men who had never seen a turbopump fire. We strip away the press releases to show you the technical reality of what humans built when they tried to leave Earth. In this 4-hour documentary, you will trace the rise and fall of the American nuclear rocket, the NERVA, hot fires at Jackass Flats, the Soviet RD-0410 that quietly beat its American counterpart, the $1.4 billion engine NASA deliberately destroyed, the Mars missions cancelled by Richard Nixon, the 180-day Mars engine that would have put humans on the surface by the year 2000. Every chapter is grounded in declassified reactor data, primary engineering archives, and the specific budget decisions that left these rockets in storage.
In December 1972, deep in the Nevada desert, engineers ignited something that shouldn't exist. For 109 minutes, longer than a full movie, a rocket engine roared like a controlled star. Inside, uranium atoms split 93 million times per second, heating hydrogen to diamond vaporizing temperatures. The ground trembled. Radiation sensors screamed. And those watching behind blast shields 2 miles away knew. We just built humanity's bridge to Mars. This wasn't some experimental prototype. The nuclear furnace ran so perfectly, so reliably, that engineers got bored monitoring it. Yet today, this revolution gathers dust in filing cabinets, a ghost haunting NASA's archives. This is the story of NERVA, the engine that could have put your parents on Mars, and why humanity chose to forget we ever built it. Every rocket ever launched fights the same losing battle against physics. Imagine throwing a baseball to the moon with just your arm. No matter your technique, your arm can't generate enough force. That's chemical rockets trying to reach Mars. Magnificent, optimized, but fundamentally limited. The Saturn V's J2 engine, which hurled Apollo to the moon, achieved 421 seconds of specific impulse. That's your rocket's fuel economy. Seconds of thrust per pound of fuel. The Space Shuttle's engine squeezed out 453 seconds. But that's it. That's the wall. Chemical bonds in hydrogen and oxygen store only so much energy. A candy bar compared to what atoms unleash. NASA's 1969 calculations revealed the absurdity. A chemical Mars mission would need to launch 800 metric tons to orbit, 6 Saturn V launches just to wave at Mars. The spacecraft would be 85% fuel, 14% structure, and 1% humans. A massive gas tank with a tiny capsule attached. But atoms don't care about chemical limits. Inside every gram of uranium-235 lurks the energy of 3 tons of coal. While chemical rockets mix liquids, nuclear fission tears apart matter itself. The numbers weren't wishful. They were inevitable. Nuclear thermal rockets promised 825 to 900 seconds of specific impulse, double what chemistry could achieve. It was like your baseball arm could suddenly reach orbit. So, in 1955, while mushroom clouds bloomed over the Pacific, a classified program began in Los Alamos. Tame the atom not to destroy cities, but to reach the stars. Project Rover was born in the same buildings as the atomic bomb. Los Alamos Scientific Laboratory, with Manhattan Project veterans, partnered with the Air Force in 1955. Could we ride nuclear fire to space? Classification was so severe scientists couldn't tell their families what they did. They just disappeared into the desert, returning home exhausted, covered in dust that set off Geiger counters. On July 1st, 1959, humanity crossed a threshold. At Jackass Flats, Nevada test site, the Kiwi A reactor went critical. Named after the flightless bird because it would never fly, KIWIA did something unprecedented. It used nuclear fission to heat hydrogen and create thrust. For 5 minutes, 70 megawatts of atomic power, enough for 50,000 homes, pushed superheated gas through a nozzle. Los Alamos director Norris Bradbury, watching through periscopes, declared, "We have liberated the atom for propulsion." Then Kennedy pointed at the moon, and everything accelerated. Though Kennedy's 1961 speech focused on beating the Soviets with conventional rockets, NASA Administrator James Webb saw further. In classified congressional testimony, Webb laid out the real vision. The moon is just practice. Mars needs nuclear rockets, or we'll never get there in our lifetimes. Project Rover suddenly had unlimited funding. Make it work, make it safe, make it fly. The desert became humanity's nuclear laboratory. Kiwi B4E, tested August 28, 1964, ran for 8 minutes at 937 megawatts, nearly a gigawatt of power. The ground shook so violently cameras 2 miles away needed stabilization. Werner von Braun, builder of the Saturn V, stood slack-jawed. His notes read, "This engine ran 10 times longer than my F1. We are seeing Mars become possible." But the real monster was Phoebus 2A. On June 26, 1968, engineers unleashed 4,082 megawatts of thermal power, over 4 gigawatts, equivalent to 4 nuclear power plants. For 12 minutes, this reactor maintained steel melting temperatures, contained building leveling forces, and did it so smoothly technicians called the test boring. Phoebus wasn't just the most powerful nuclear reactor ever built. It proved atomic rockets had graduated from theory to reality. But building a nuclear reactor was one thing. Making it light enough to fly, safe enough for astronauts, and reliable enough to restart in deep space was an engineering challenge that would define the entire Apollo decade. Harold Finger had an impossible job. As director of the Space Nuclear Propulsion Office, he had to contain 3,000-degree hydrogen, hot enough to turn tungsten into vapor, inside a flying nuclear reactor. His solution, like science fiction, worked like clockwork. Hexagonal fuel elements, pencil-sized, riddled with 19 spaghetti-thin cooling channels. Liquid hydrogen, at minus 253 degrees Celsius, would flow through these channels, stealing heat from the uranium, then blast out the nozzle at velocities that made chemical rockets look lazy. The hydrogen wasn't just propellant. It was coolant, moderator, and radiation shield. This wasn't theoretical. Between 1964 and 1969, engineers tortured over 20 different fuel element designs, subjecting them to temperature swings that would shatter wine glasses. They heated them to 2,500 degrees, cooled them to absolute zero, then heated them again and again. 60 thermal cycles, each a journey from Arctic cold to solar furnace heat. On December 15, 1967, NRX A6 showed what persistence could achieve. The engine ran for 62 minutes straight, over an hour of continuous nuclear thrust. For perspective, the Saturn V's F1 engines burned for 168 seconds. NERVA ran 22 times longer, maintaining power with less than 1% variance. NASA's technical report described it with unusual emotion, unprecedented success in all parameters. But XE Prime was the masterpiece. Tested 3 days after Apollo 11 splashed down, this wasn't just a reactor. It was a complete propulsion system. Turbopumps whirred. Actuators responded. Control systems computed. On December 11, 1969, XE Prime demonstrated 28 restart cycles, throttling from quiet 20% power to full nuclear fury and back. It accumulated 115 minutes of operation, proving nuclear rockets weren't just powerful, they were practical. Program manager Milton Klein told reporters, "XE Prime is not a prototype. This is flight hardware. We could bolt this engine to a rocket tomorrow and fly to Mars. The cost for this revolution? $1.4 billion over 17 years. Less than NASA spent on the Saturn V's paint." NERVA was delivering science fiction capabilities for hardware store prices. By 1969, with XE Prime purring in the desert, NASA drew up blueprints for nuclear Mars ships. Not someday dreams, but engineering documents stamped ready for production. NASA's Integrated Program Plan, delivered to President Nixon on September 15, 1969, wasn't a wish list. It was an instruction manual for conquering the solar system. The 500-page document, buried in archives, detailed nuclear shuttles by 1978, a permanent moon base by 1980, and boots on Mars by November 1982. These were schedules based on existing hardware. The elegance was breathtaking. Replacing the Saturn V's third stage with a NERVA engine would catapult payload capacity to Mars from 30 tons to 75 tons. Imagine moving your house with a pickup versus a semi-trailer. That's the difference NERVA made. Travel time would shrink from 260 days to 180 days, meaning astronauts would absorb 30% less cosmic radiation, arriving healthier, ready to explore. Wernher von Braun became NERVA's prophet. Before Congress in November 1969, the man who sold America on the moon now preached nuclear salvation. Chemical rockets give us flags and footprints on Mars. Nuclear rockets give us cities. His team ran 10,000 computer simulations using real XE Prime data. The conclusion: NERVA could deliver a complete Mars base in just 3 launches. The nuclear shuttle concept was even bolder. These atomic workhorses would live in space, ferrying cargo between Earth and Moon like orbital semi-trucks. Boeing showed each shuttle could make 10 round trips before refueling, cutting lunar base resupply costs by 68%. The Moon would become a gas station, Mars a suburb. Then, on January 5, 1973, a single paragraph from the Office of Management and Budget murdered the future. The NERVA program is terminated effective immediately. The reasoning was bureaucratic brutality. All technical objectives have been met or exceeded. The engine is ready for flight development. However, there are no planned missions requiring this capability. Senator William Proxmire, NERVA's executioner, delivered the eulogy. "We're spending millions to reach Mars while poverty exists on Earth. The nation that spent $25 billion reaching the moon couldn't find $200 million to finish the engine that would take us beyond it." NERVA died not from failure, but from succeeding at the wrong moment. But atoms have patience, and physics doesn't forget. Because 50 years later, the nuclear rocket has risen from its grave. And this time, it's brought friends. On May 25, 2019, NASA Administrator Jim Bridenstine stood at Marshall Space Flight Center and spoke words that would have seemed heresy. NASA is going nuclear. Again. The agency unveiled Draco, demonstration rocket for agile cislunar operations, targeting a nuclear thermal propulsion demonstration by 2027. After half a century of exile, the atom was returning to space. Geopolitics had shifted. In January 2019, China's Chang'e 4 landed on the moon's far side, planting their flag where no one could see it, a metaphor for their ambitions. Their roadmaps showed nuclear cargo ships supporting lunar cities by 2035. Russia announced their nuclear-powered space tug in 2018, claiming it would make chemical rockets as obsolete as sailing ships. The space race had returned. A marathon, not a sprint. Lockheed Martin won the Draco contract in July 2023, partnering with BWX Technologies, builders of reactors for nuclear submarines. Kirk Shireman, Lockheed's Lunar Exploration VP, made a startling admission. We're not inventing anything. We're copying homework from 1972. NERVA solved every problem we're facing. The technology Resurrection is remarkable. Modern triso fuel particles, ceramic spheres the size of poppy seeds, can withstand 1,600 degrees Celsius, solving NERVA's Achilles heel of fuel erosion. Each particle is its own containment vessel, wrapped in carbon and silicon carbide. General Atomics' new reactor design using these particles promises 900+ seconds of specific impulse, double any chemical rocket. Ultra safe. Nuclear Corporation's Michael Eads captures the irony. NERVA engineers with slide rules achieved what we're struggling to match with supercomputers. They'd weep seeing our materials. Carbide composites that laugh at temperature. 3D printing. Computer modeling. We're not surpassing NERVA. We're catching up. Which forces us to confront the equation that keeps physicists awake at night. If NERVA had continued developing for 50 years, where would humanity be today? The mathematics of lost opportunity is suffocating. NERVA was flight-ready in 1972. With continuous development, Mars cargo missions would have been routine by 1990. Permanent Mars bases with 1,000 residents were achievable by 2010. Nuclear propulsion makes asteroid mining profitable. The delta V to reach near-Earth asteroids drops from impossible to trivial. We could have been harvesting trillion-dollar rocks since the 1990s, birthing space industry. The International Space Station could have been built in 3 years with 8 nuclear shuttle flights. O'Neill cylinders, those magnificent space colonies, transform from fantasy to engineering projects when launch costs plummet 80%. We could be living in space cities now. Here's the cruelest calculation. Fusion propulsion. The ultimate cosmic engine requires massive space infrastructure. With nuclear thermal rockets providing cheap access to orbit, fusion experiments could have proceeded in space since the 1980s. We might today be launching interstellar probes instead of struggling to return to the moon. So, we're left staring at NERVA's ghost. A perfect engine that worked too well for its own good. Somewhere in the Nevada desert, Test Cell C stands like a concrete cathedral. The rails that carried NERVA engines are rust orange but strong enough to hold another rocket. The control room sits empty, except for tumbleweeds and memories. These aren't monuments to failure. They're monuments to a future we built, tested, perfected, and then abandoned. NERVA proved something profound. Barriers to human expansion aren't technological. They're psychological. We didn't abandon nuclear rockets because they failed. We abandoned them because we succeeded and then lost the courage to use our success. The engine that ran perfectly for 109 minutes in 1972 could have been pushing spacecraft to Mars by 1975. Instead, it was dismantled, studied, and filed away like a letter from a future we decided not to visit. Today, as we resurrect this technology with Draco, we're not pioneering. We're remembering. The bitter comedy is that modern nuclear thermal rockets, for all their supercomputers and miracle materials, are still trying to match what engineers achieved with slide rules and raw determination in the Nevada desert. Stan Borowski, NERVA's keeper of the flame, offers the perfect epitaph. Every Mars study eventually rediscovers NERVA. It's not whether we'll use nuclear propulsion. It's whether we'll admit we need what we already perfected. What do you think would be different today if NERVA had powered our space program for the last 50 years? Would we be walking on Mars? Mining asteroids? Or would we have found new ways to abandon our dreams? And now that we're bringing nuclear propulsion back from the dead, will we have the courage to use it this time? Or will we bury it again? Let me know your thoughts below. And tell me which abandoned space technology deserves resurrection next. If you want more stories of futures we threw away, hit subscribe. Until next time, keep looking up and remember, somewhere in a filing cabinet, the blueprints for our cosmic future are waiting. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.
In 2003, just months after the Columbia disaster shook NASA to its core, the agency unveiled an ambitious plan: a school bus-sized spacecraft powered by a nuclear reactor that would generate more electricity than all previous planetary missions combined. The Jupiter Icy Moons Orbiter would be so powerful, it could hop between Jupiter's moons like a hummingbird, sipping nectar from flower to flower, searching for alien life in subsurface oceans. 2 years later, it was dead, canceled to fund another program that would also be canceled. This is the story of how NASA resurrected a Cold War dream, only to watch it die the exact same death, proving that some lessons are never learned. The question isn't whether we can build a nuclear spacecraft. It's whether we can ever escape the gravitational pull of our own politics long enough to actually launch one. Picture this. It's 2003, and while the nation mourns Columbia, a small team at the Jet Propulsion Laboratory is sketching plans for a spacecraft that would make the Apollo program look quaint. They're not just designing a machine to visit Jupiter's moons. They're designing one that will move in with them. They called it the Jupiter Icy Moons Orbiter, and on paper, it was magnificent. At 20,000 kilograms fully fueled, imagine 4 full-grown elephants strapped to a rocket, JIMO would be one of the most massive planetary spacecraft ever conceived. A flying laboratory powered by something NASA hadn't touched in 3 decades, a nuclear reactor. But not the plutonium batteries that had powered Voyager and Cassini with their modest hundreds of watts, barely enough to run a few light bulbs. No, this was a full-fledged fission reactor generating between 100 and 200 kilowatts of electrical power. Enough to run a small neighborhood. Enough to power a high school. Orders of magnitude more than any previous deep space mission, all focused on a single audacious goal: answering whether we're alone in the universe. Because here's what drove Charles Alaki and his team at JPL forward. The National Academy of Sciences had made it clear that Europa, Ganymede, and Callisto weren't just frozen rocks. They harbored subsurface oceans, liquid water, potential habitats for life. And reaching them, really studying them, exceeded the capabilities of any solar-powered mission humanity could build. Think about it this way. Jupiter orbits 5 times farther from the Sun than Earth does. That means sunlight there is 25 times weaker. Not 5 times, but 5 squared. Solar panels that could power a spacecraft in Earth orbit become as useful as a flashlight in a cave. You're working in permanent twilight, trying to run a flying laboratory that needs to operate for a decade without maintenance, in the most hostile radiation environment in the solar system. Solar power wasn't just impractical, it was impossible. This is where JIMO became something more than a spacecraft. It became a hummingbird designed to sip nectar from 3 different flowers in the deadliest garden in the solar system. The nuclear reactor would feed high-power ion engines with a delta VI budget exceeding 10 kilometers per second. That's over 22,000 miles per hour of maneuvering capability. Enough to perform unprecedented orbital gymnastics, spiraling from moon to moon like a cosmic ballet dancer, each movement precise, each destination months of intensive study. Scientists like Robert Pappalardo envisioned a mission that wouldn't just fly by these worlds at 30,000 miles per hour, stealing a few precious hours of data like a thief in the night. JIMO would actually orbit each moon, spending months, perhaps years, mapping their ice shells with penetrating radar, measuring their magnetic fields with sensitive magnetometers, analyzing their surface compositions with spectrometers operating across infrared, ultraviolet, and visible wavelengths. Every wavelength of light would become a different pair of eyes, each one revealing secrets invisible to the others. The planned operational phase stretched 6 to 8 years in the Jovian system itself. 6 to 8 years of continuous science, of daily discoveries, of watching these alien worlds transform from fuzzy telescope dots into places we could know as intimately as we know our own moon. The data rates, 10 to 50 megabits per second, enabled by all that nuclear-generated power, would return several terabits of science data. To put that in perspective, that's more data than Galileo collected in its entire 14-year mission, delivered every few months. Every instrument, every system, every line of code was designed around a single premise: that with unlimited power, humanity could finally answer whether we're alone. The engineers weren't just building a spacecraft, they were building a key to unlock doors we'd been staring at for decades. On paper, JIMO was perfect. The reactor would provide unlimited power. The ion engines would provide unlimited maneuverability. The instruments would provide unlimited science. But there was a problem that everyone knew, but few wanted to acknowledge. NASA had tried this before. In the 1960s, Project NERVA developed nuclear rocket engines that worked perfectly. Then Congress killed the program anyway. The engineers pushing JIMO forward were either unaware of this history or believed things would be different this time. They were wrong. Here's what the glossy mission brochures didn't show: the late-night meetings where engineers admitted they didn't know if their reactor could survive a decade in deep space. The simulations that kept showing the high-voltage systems arcing in ways that could fry the entire spacecraft. The growing realization that they were trying to build a nuclear power plant that could fly. Jupiter's radiation environment is a monster. Imagine standing next to an industrial X-ray machine, the kind they use to inspect welds and steel beams, except it's running continuously, and you can never turn it off or step away. Now imagine that machine is the size of a planet. That's Jupiter's magnetosphere. Magnetic fields and particle belts so intense they make Earth's Van Allen belts look like a gentle breeze. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, was heavily shielded and still barely survived, its electronics slowly degrading with each orbit like a fighter taking body blows round after round. JIMO's designers knew they'd need unprecedented shielding, thick aluminum vaults to protect the avionics, radiation-hardened electronics that had never been tested at this scale. But shielding was only half the problem. That nuclear reactor, churning out 100 to 200 kilowatts of continuous power, would generate waste heat that had to go somewhere. The solution? Deployable radiators capable of rejecting over 100 kilowatts of thermal energy. Imagine keeping a steel mill cool without air conditioning, in the coldest part of winter, except there's no air at all and you're 500 million miles from the sun. In space, you can't use fans or coolant towers or any of the tricks we use on Earth. Heat can only escape through radiation, infrared light bleeding into the void. You need radiators the size of billboards, unfolding like metallic flowers, glowing dull red in the darkness. And then there was the voltage problem. To efficiently distribute that much power across the spacecraft, you needed high-voltage systems operating in the vacuum of space. Here's the nightmare. In a vacuum, electricity doesn't behave the way it does on Earth. Insulation that works perfectly in atmosphere becomes treacherous. Plasma interactions create unpredictable arcing. One wrong spark, one microscopic flaw in a wire's coating, and you could lose the entire power bus, turning your billion-dollar spacecraft into an expensive paperweight orbiting Jupiter, forever silent. The Department of Energy's Naval Reactors Laboratory was tasked with developing this megawatt-class reactor technology, but they were venturing into territory where the rulebook hadn't been written yet. New materials, new power management schemes. Everything was never before attempted. Every solution created two new problems. Every test revealed 3 new failure modes. Internal NASA meeting minutes from this period reveal something fascinating. The engineers weren't all singing from the same hymn sheet. Some pushed for incremental steps, technology demonstrators, proof-of-concept missions, anything to reduce the risk before betting everything on a flagship mission. We're chasing a dream that's too expensive and too risky, some argued in closed-door meetings. The technology just isn't there yet. Others argued the opposite. Go big or go home. Only an ambitious goal could justify the investment, could capture the public imagination, could secure the funding stream. These weren't just technical debates. They were philosophical disagreements about how NASA should operate in the post-Columbia era. Risk-averse versus risk-tolerant. Incremental versus revolutionary. The ghost of Challenger and Columbia haunted every conversation. How much risk was acceptable when the stakes were this high? The cost estimates reflected this uncertainty. $3 billion on the optimistic end, $10 billion on the pessimistic, $15 billion if things went really wrong. And here's what nobody outside the program really understood. Much of that uncertainty stemmed from the fact that they were developing not just a spacecraft, but an entire infrastructure. The reactor was designed to be modular, reusable for future outer solar system missions to Saturn, Uranus, Neptune, worlds where sunlight becomes a distant memory, and nuclear power transforms from luxury to necessity. The innovations in radiator design, in heat pipe technology, in autonomous navigation, these were investments that could pay dividends across decades of exploration. But you had to survive long enough to prove the concept. You had to make it to the launch pad. By 2004, the National Research Council was sounding alarm bells. The technology wasn't mature, the timeline was unrealistic, and the cost? Well, the cost was about to become someone else's problem. Because NASA had a new priority, and it was wearing a very familiar face. Imagine you're a young engineer, fresh out of graduate school, joining NASA in 2003 with dreams of working on GMO, the mission that would define your generation. You spend 2 years of your life designing radiation shielding systems, running simulations until 2 a.m., solving problems that have never been solved before. You're building something that will outlive you, that will answer questions humans have asked since we first looked up at the stars. Then you walk into work one morning in February 2005, and it's over. NASA officially canceled JIMO. The cancellation significantly impacted the team. The official reason? Budgetary constraints and programmatic priorities. Bureaucratic language for, "We found something more politically popular." The Constellation program had arrived. President Bush's grand vision to return humans to the moon and eventually Mars. Sound familiar? It should. It's the exact same script that killed NERVA 3 decades earlier. Sacrifice the distant science mission for the politically popular human spaceflight program. Boots on the ground sell better than robots in orbit. Flags and footprints win elections. The search for alien life in subsurface oceans? That's a harder story to tell in a 30-second campaign ad. For the younger engineers and scientists who had joined NASA specifically to work on JIMO, who'd turned down private sector jobs and relocated their families to chase this vision of nuclear-powered exploration, the professional and emotional heartbreak was acute. One moment you're designing humanity's first nuclear-powered tour of the outer solar system, solving problems that have never existed before. The next, you're updating your resume, watching years of work reduced to PDF files on a server nobody will ever access. By 2008, even the remnants of Project Prometheus, GMO's parent program, were completely defunded. The nuclear dream was dead. Again. The cruel irony? Later studies showed JIMO's technology was actually feasible. NASA's kilopower reactor project in the 2000s proved the concept worked. Small nuclear reactors could operate reliably in space, providing kilowatts of continuous power for years. The engineering challenges that seemed insurmountable in 2005 were solvable. We could have had answers by now. We could have known whether life exists in Europa's ocean, whether Ganymede's subsurface sea harbors anything more than water and salt. whether Callisto's ancient ice holds secrets frozen since the solar system's birth. Instead, we're still waiting, still planning, still dreaming of missions that may never launch. All that remains of JIMO are dusty design documents, unused prototypes gathering dust in JPL warehouses, and a generation of scientists who wonder, what if? What if the funding had held? What if Constellation hadn't consumed NASA's budget like a black hole? What if we'd chosen the Hummingbird over the moon rocket? But the damage went deeper than individual careers or canceled hardware. JIMO's cancellation fundamentally altered NASA's institutional psychology. The agency became more skeptical of large, high-risk flagship missions, especially those dependent on immature technologies. The public and regulatory scrutiny of nuclear space propulsion intensified. Every future proposal would now carry the baggage of Project Prometheus, another expensive nuclear dream that never left the ground. NASA retreated to safer ground, modular development, incremental technology demonstrations, missions that could survive budget fluctuations without collapsing entirely. The era of betting everything on a single revolutionary spacecraft was over. The age of caution had begun. Yet here's where the story gets complicated, because JIMO didn't die without leaving fingerprints all over the future. The radiation shielding designs, they informed power systems for Artemis lunar habitats, protecting future astronauts from cosmic rays and solar storms. Those ambitious scientific goals and instrument concepts, they shaped Europa Clipper's entire mission architecture when it finally launched in 2024. The risk assessment frameworks developed for Prometheus became standard operating procedure for NASA's current nuclear thermal and nuclear electric propulsion initiatives aimed at getting humans to Mars in the 2030s. The innovations in heat pipe technology, autonomous navigation, and fault detection didn't vanish. They migrated, evolved, found new homes in missions that could actually fly. JIMO became a ghost, but a productive ghost, haunting every subsequent mission with whispers of what might have been and lessons about what not to do. Europa Clipper represents a different approach, utilizing solar power and flybys to mitigate the risks and costs associated with a nuclear-powered orbiter, like JIMO. It's solar-powered, not nuclear. It flies by Europa dozens of times instead of orbiting for years. It's safer, cheaper, more politically palatable. It's what you build when you've learned that sometimes good enough is better than perfect, if perfect means never launching at all. Here's the cruel irony. The Constellation program that killed JIMO canceled in 2010. 5 years of work, billions of dollars spent, and nothing to show for it except another lesson that apparently nobody learns. We traded the Hummingbird for a moon rocket that never flew, sacrificing the possible for the politically expedient. Meanwhile, the same type of reactor technology that could have unlocked the secrets of Europa in the 2010s is now being proposed again for Mars missions in the 2030s. We're still drawing the same blueprints, still having the same debates, still making the same promises. Different decade, different destination, same cycle, initial enthusiasm, technical challenges, cost overruns, political shift, cancellation. The only question is whether this time will be any different. We began with the promise of a revolutionary spacecraft that would unlock the secrets of alien life. But we've discovered something far more sobering. The greatest barrier to space exploration isn't engineering. It's us. JIMO's failure wasn't about technology. The reactor could have worked. The shielding could have been built. The ion engines could have spiraled between those moons like a cosmic ballet. The science was sound. The engineering was feasible. The only thing that failed was our collective will to see it through when the political winds shifted. The same forces that killed NERVA in the 1960s killed JIMO in the 2000s, and they're still killing ambitious missions today. Until we solve the problem of political gravity, until we learn to commit to long-term scientific goals that outlast election cycles and budget negotiations, our boldest dreams will keep dying on the launch pad. Somewhere in the Jovian system, beneath miles of ancient ice, an alien ocean might be teeming with life, waiting for us to ask the question we've been too distracted to ask. JIMO could have given us the answer. Instead, it's just another ghost, haunting the graveyard of missions that could have changed everything. The technology was ready. The science was sound. We just weren't ready for ourselves. And that's the most terrifying discovery of all, that the final frontier isn't out there among the stars. It's right here, in the space between our ambitions and our willingness to pay for them. Between what we dream and what we're willing to sacrifice to make those dreams real. Between the hummingbird we could have built and the compromises we chose instead. Europa Clipper launches in 2024, NASA's latest attempt to study Jupiter's icy moons, though without JIMO's nuclear power or ability to orbit multiple moons. Will it make it, or will it join JIMO in the graveyard of canceled dreams? What mission do you think NASA should prioritize, and what would you be willing to sacrifice to make it happen? The cosmos is full of mysteries, but sometimes the biggest mystery is why we keep making the same mistakes. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching. On January 12, 1965, America's brightest nuclear scientists gathered in the Nevada desert to witness something unprecedented, the deliberate destruction of a perfectly functioning nuclear reactor. This wasn't an accident. It wasn't a failure. It was the plan. The Kiwi TNT reactor sat on its test stand, designed from the ground up to explode. A controlled catastrophe meant to answer one terrifying question. What happens when humanity's most powerful rocket engine fails in the worst possible way? What they discovered that day would haunt the space program for decades and ultimately determine whether humanity would ever ride atomic fire to the stars. To understand why anyone would deliberately destroy a working nuclear reactor, you have to go back to a dream that consumed an entire generation of physicists and engineers. In the aftermath of World War II, as the space age dawned, America's rocket scientists faced a fundamental problem. Chemical rockets were never going to take us to Mars. They were too slow, too heavy, too limited by the basic chemistry of burning fuel. But there was another way. A revolutionary technology that promised to change everything. Project Rover began in 1955 with a deceptively simple idea. Instead of burning chemical fuel, why not use a nuclear reactor to superheat hydrogen propellant to temperatures that would make conventional engines melt into slag? The physics were elegant, almost seductive in their efficiency. A nuclear thermal rocket could achieve specific impulses of 800 to 900 seconds, roughly double the performance of the best chemical rockets, which topped out around 400 seconds. That difference wasn't just incremental, it was transformational. It was the difference between being trapped in Earth orbit and reaching the outer planets. It was the difference between Mars being a distant dream and Mars being a destination. Dr. Ted Merkel, one of the project's leading engineers, became obsessed with what he called the technical sweetness of nuclear propulsion, the raw power, the elegant physics, the sheer efficiency that made chemical rockets look primitive by comparison. The Kiwi reactors, named after the flightless bird in a bit of dark humor about a technology that might never fly, represented years of incremental success. Each test brought new breakthroughs. Each problem solved revealed new possibilities. By 1964, the Kiwi B4A reactor had been successfully tested, proving that the fundamental concept worked. The graphite-moderated, hydrogen-cooled engine could superheat propellant to temperatures that would vaporize steel. The technical challenges that would have stopped lesser engineers, thermal stress, material erosion, the brutal environment inside a reactor core, pumping liquid hydrogen at cryogenic temperatures, had been solved, one by one. The dream of atomic spaceflight wasn't just possible anymore. It was real, sitting on a test stand in the Nevada desert, ready to carry humanity to the stars. But there was one question that kept nuclear propulsion grounded, one scenario that haunted mission planners in their sleep. What happens during a launch abort? What if something goes catastrophically wrong during ascent? What if the reactor goes critical uncontrollably, not in the controlled environment of a test stand, but tumbling through the atmosphere over populated areas? No one actually knew the scale of the catastrophe that would follow. Computer models could only tell you so much. Real-world physics always has surprises, and with nuclear reactors, surprises can kill thousands. To answer that question, to truly understand the monster they had created, Merkel and his colleagues would have to do something unprecedented. They would have to deliberately trigger the very nightmare scenario they hoped would never happen. Engineering a disaster is harder than you might think. The Kiwi reactors had been designed with multiple layers of safety systems, each one carefully crafted to prevent exactly the kind of catastrophic failure they now needed to create. Transforming the Kiwi B4A into Kiwi TNT required inverse engineering, deliberately weakening systems that had taken years to perfect, removing the safety nets that stood between controlled operation and explosive disassembly. The modifications were precise and calculated. They altered the moderator cylinders and increased the reactivity insertion rate, ensuring the reactor would achieve what nuclear engineers call prompt criticality, the rapid exponential increase in reactor power that occurs when the nuclear chain reaction runs away faster than any safety system can respond. The team calculated the exact sequence: withdraw the control rods rapidly, flood the core with liquid hydrogen propellant, and let physics do the rest. The expected energy release, equivalent to approximately 1 ton of TNT. Not a nuclear weapon, but a thermal explosion violent enough to tear the reactor apart and scatter its radioactive contents across the desert. There's a story about Dr. Ted Merkel that captures the all-consuming nature of this work, the way it invaded every corner of life. As his wife went into labor, Merkel sat in the hospital waiting room, drawing blast radius circles on maps of potential launch sites, calculating fallout patterns while awaiting his child's birth. It's a moment that crystallizes the tension between personal life and scientific duty, between the intimate human scale of a father waiting for his child and the vast, impersonal calculations of radioactive dispersal and acceptable risk. But there was another variable they couldn't fully control, one that would determine whether this experiment remained a scientific milestone or became a public relations disaster: the radioactive fallout. The Kiwi reactor core contained about 40 kilograms of highly enriched uranium and several kilograms of fission products from previous test runs. During prompt criticality, as the core temperature spiked to over 4,000 Kelvin, hot enough to vaporize a significant portion of the graphite and metal, all of that radioactive material would be released into the atmosphere uranium particles. Fission products, a complex cocktail of radioactive isotopes including iodine-131, cesium-137, and strontium-90, each with its own half-life, its own biological pathway, its own capacity for harm. Radioactive dispersal is notoriously unpredictable. Wind speed, atmospheric stability, particle size distribution, all variables that could expand or contract the danger zone. The Nevada test site was chosen specifically for its remoteness and prevailing wind patterns that typically carried fallout away from populated areas. But typically isn't always. Weather forecasts in 1965 were far less sophisticated than today, introducing significant uncertainty into every calculation. The environmental scientists and health physicists who had to model the radioactive dispersal found themselves caught between their duty to enable the test and their responsibility to protect public health. Their calculations revealed uncomfortable truths about acceptable risk. The expected radius of radioactive fallout and contamination was up to 50 miles downwind for direct environmental sampling, with detectable fallout potentially reaching as far as 200 miles. These weren't just technical questions, they were moral ones. How much radioactive contamination of downwind areas was acceptable? How many people could be exposed to how much radiation before the test became unconscionable? The answers were classified at the highest levels. The test itself was wrapped in secrecy, with public information carefully controlled to avoid panic about nuclear explosions in Nevada. The political clearances were secured. The environmental models were complete, however uncertain. There was nothing left to do but execute the test. January 12, 1965, dawned cold and clear over the Nevada test site. Final weather checks confirmed acceptable conditions. Not ideal, but acceptable. There's always a compromise between perfect conditions and schedule pressure, between waiting for the optimal moment and the institutional momentum that demands results. Personnel evacuated to bunkers and observation points miles away, leaving only remote cameras and instrumentation near the test stand to witness what came next. Dr. Harold Agnew, the senior physicist who had championed this test, watched from the control bunker with what he would later describe as a mixture of excitement and apprehension. This was the moment when theoretical physics becomes visceral reality, when equations transform into shock waves, when the elegant mathematics of neutron cross-sections and thermal expansion coefficients become fire and fury in the real world. The countdown sequence began. Liquid hydrogen began flowing into the reactor, a river of cryogenic fuel at minus 253 degrees Celsius, so cold it would freeze air solid. Cooling systems activated. Then the critical moment. The control rods withdrew rapidly, far faster than any normal startup sequence would allow. The nuclear chain reaction began, neutrons splitting uranium atoms, releasing more neutrons, splitting more atoms, the reaction rate doubling and doubling again in a runaway cascade. Within 1.5 seconds, the reactor achieved prompt criticality. The core temperature spiked to over 4,000 Kelvin, hot enough to vaporize the graphite moderator, hot enough to dissociate hydrogen molecules into individual atoms. The thermal expansion was instantaneous and violent. Hydrogen pressure built faster than the reactor vessel could contain. The explosive disassembly tore the reactor apart with a force equivalent to approximately 1 ton of TNT. A fireball erupted from the test stand, a sphere of incandescent gas expanding at supersonic speed. Debris, chunks of graphite, twisted metal, vaporized uranium, scattered in all directions. A mushroom cloud rose into the Nevada sky, smaller than a nuclear weapon's signature, but unmistakably similar in form. The cameras captured it all, frame by frame, the destruction unfolding in slow-motion clarity. The explosion was more violent than some predictions suggested. Debris scattered across a wider radius than certain models had indicated. Instrumentation designed to survive the initial blast was destroyed faster than expected. In those first seconds, it became clear that even with all their calculations, all their modeling, all their careful engineering, nature had delivered surprises. But the explosion itself was only the beginning. The real test, the real danger, was what came next. The fallout. Radiation monitors detected the plume immediately, tracking its movement across the desert. The vaporized uranium and fission products created a complex mix of radioactive isotopes, each one carried by the wind in patterns that defied simple prediction. Particulate matter settled in unpredictable ways. Some areas showed hotspots far from the test site due to local weather anomalies, microscale variations in wind and terrain that no model could have captured. The actual path and deposition of the radioactive fallout plume differed from predicted models, traveling farther and depositing measurable contamination in areas not originally expected, including southern Nevada and California. Measurable levels of radioactive isotopes appeared in milk and air samples up to 200 miles downwind. Public health agencies tracked the dispersal, documenting contamination levels that, if publicly known at the time, would have sparked significant controversy. Cleanup crews faced contaminated debris scattered across the test site, twisted metal, chunks of graphite, fragments of the reactor vessel, all of it radioactive. Some pieces would remain dangerous for years, slowly decaying as their constituent isotopes transformed into more stable forms. The half-life of cesium-137 is 30 years. Strontium-90, which mimics calcium and accumulates in bones, has a half-life of 29 years. The Kiwi TNT test site would be a radioactive scar on the Nevada desert for decades. Despite the violence of the explosion, despite the surprises in the fallout patterns, the test was deemed a technical success. They had successfully modeled a worst-case reactor failure. They had gathered data on radioactive dispersal under real-world conditions. They had answered the question they set out to answer. But the answer was one that NASA and the Atomic Energy Commission didn't want to hear. The data revealed an uncomfortable truth. Even a controlled nuclear disaster in a remote desert produced radioactive contamination that couldn't be fully contained or predicted. The environmental and health risks highlighted by the test contributed to growing opposition and skepticism regarding the safety and practicality of nuclear rocket programs. If this had happened during an actual launch abort, over Cape Canaveral, over the Atlantic, over any populated area, the consequences would have been catastrophic on a scale that made the entire enterprise politically untenable. The Kiwi TNT test had answered the question it was designed to answer. But sometimes, proving you can control a disaster is the same as proving you shouldn't risk it at all. The death of the dream was slow, a gradual erosion rather than a sudden collapse. Additional reactor tests continued after Kiwi TNT. The NERVA program, nuclear engine for rocket vehicle application, followed Project Rover, developing even more advanced designs, pushing the technology closer to flight-ready status. The engineers achieved remarkable technical successes, solving problem after problem, proving again and again that nuclear thermal propulsion could work. But the fundamental problem remained unsolved. How do you make a nuclear rocket safe enough for public acceptance? The political climate was shifting. The 1963 Partial Test Ban Treaty had already banned atmospheric nuclear tests, and public sentiment was turning against nuclear activities that posed environmental risks. The specter of nuclear proliferation loomed over every discussion. Nuclear thermal rockets used highly enriched uranium, the same material used in nuclear weapons, and any launch failure could scatter weapons-grade material across a wide area. Environmental groups and public health advocates, learning of tests like KIWI-TNT through leaks and declassifications, began raising fundamental questions about the wisdom of launching nuclear reactors through the atmosphere at all. Dr. Ted Merkel and the project team faced the reality that their life's work, the reactor designs they'd perfected, the technical problems they'd solved, the elegant physics they'd mastered, might never fly the psychological toll of seeing a revolutionary technology shelved not because it didn't work, but because it worked too well, too dangerously, was profound. These were engineers who had dedicated years to solving impossible problems, only to discover that the real impossible problem was political and social, not technical. In 1973, Project Rover was canceled. The official reason cited was budgetary constraints and changing national priorities, particularly the end of the Apollo program and reduced interest in crewed Mars missions. But everyone involved knew the deeper truth. The environmental and political costs were deemed too high. The total program cost had exceeded $1.4 billion in 1972 dollars, a staggering investment that produced working nuclear rocket engines that would never fly. The tragic irony of Kiwi TNT is that it proved both too much and too little. It proved that the worst-case scenario was survivable and measurable, that scientists could understand and model a catastrophic reactor failure. But in doing so, it made the worst-case scenario real and tangible for policymakers and the public. It transformed an abstract risk into concrete data about radioactive contamination spreading hundreds of miles, about unpredictable fallout patterns, about the impossibility of guaranteeing safety when dealing with nuclear reactions in the atmosphere. The legacy of Kiwi TNT extends far beyond the Nevada test site, far beyond the canceled programs and the billions of dollars spent. It represents a fundamental question that still haunts space exploration today. How much risk is acceptable in the pursuit of the stars? How do we balance the revolutionary potential of dangerous technologies against the responsibility to protect the environment and public health? The nuclear rocket engines developed under Project Rover and NERVA were engineering marvels, machines that could have cut travel time to Mars in half, that could have opened the outer solar system to human exploration. They worked, they were real, and they will probably never fly, not because we can't build them, but because we chose not to accept the risks they represent. That choice, made in the shadow of Kiwi TNT's mushroom cloud, informed by data about radioactive dispersal and environmental contamination, reflects a maturation of the space program, a recognition that technical capability alone doesn't justify deployment. Sometimes the most important scientific result isn't a number or a measurement, but a decision about what not to do. The Kiwi TNT test site remains in the Nevada desert, a radioactive monument to ambition and restraint, to the dream of atomic spaceflight and the reality of environmental responsibility. The reactor fragments have long since been cleaned up or buried, but the isotopes remain, slowly decaying, slowly releasing their energy into the desert sand. In a few more decades, the cesium-137 will have decayed to half its original activity. In a century, it will be mostly gone. But the question Kiwi TNT raised will remain, what are we willing to risk to reach the stars? What price in environmental damage, in public safety, in the possibility of catastrophic failure is acceptable for revolutionary capability? These aren't questions that science alone can answer. They require us to confront our values, our priorities, our vision of what humanity should become as we reach beyond our planet. On January 12, 1965, America's brightest nuclear scientists deliberately destroyed a perfectly functioning nuclear reactor to answer one question. They succeeded. The answer they found changed the course of space exploration, not through failure, but through a success that revealed costs we were unwilling to pay. The mushroom cloud that rose over Nevada that day cast a shadow that still falls across our dreams of Mars, of the outer planets, of the deep space missions that nuclear propulsion could enable. Perhaps one day, with better technology, with safer designs, with a different calculus of risk and reward, nuclear rockets will finally fly. But they will fly, if they fly at all, because we learned the lessons of Kiwi TNT, that power without wisdom is dangerous, that technical capability without social acceptance is unusable, and that sometimes the bravest thing scientists can do is acknowledge the limits of what should be built, not just what can be built. The dream of atomic spaceflight didn't die in the Nevada desert on January 12, 1965. It was transformed, tempered by the reality of radioactive fallout spreading 200 miles downwind, by the recognition that some technologies demand more careful consideration than others. Kiwi TNT was designed to fail catastrophically, and it succeeded perfectly. In doing so, it taught us that not every success is worth celebrating, and not every capability is worth deploying. That lesson, purchased at the cost of $1.4 billion and a radioactive scar on the Nevada desert, may be the most valuable result of the entire nuclear rocket program. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.
In January 1965, deep in the Nevada desert at Jackass Flats, engineers deliberately destroyed a nuclear rocket engine. They brought Kiwi TNT to full power in seconds, far faster than any safety protocol allowed, and watched as the reactor core tore itself apart. The explosion sent radioactive fuel fragments across the test site. Hydrogen flames erupted. Contamination spread downwind across an area the Atomic Energy Commission would later classify. This was not an accident. This was a test. They destroyed a nuclear rocket engine on purpose to understand what happens when these machines fail catastrophically. And then they classified almost everything about what they learned. If you're interested in the real story behind space programs, the technology that actually flew, the decisions that never made the press releases, and how space became a strategic domain, subscribe to Space Cluster, like, and turn on notification. We focus on what was built, why it mattered, and where it really led. Now, back to the story. For 14 years, from 1959 to 1973, the United States operated the most ambitious nuclear propulsion program in history. Project Rover was the umbrella designation for a series of ground tests that would culminate in NERVA, the nuclear engine for rocket vehicle application. The goal was straightforward: develop a nuclear thermal rocket capable of sending humans to Mars. The reality was far more complex, far more dangerous, and far more heavily classified than the public ever knew. The basic principle seemed elegant. Take a nuclear reactor. Run liquid hydrogen through the core. The hydrogen heats to extraordinary temperatures and exhausts through a nozzle, producing thrust. No combustion, no chemical propellants, just physics. The specific impulse would be double that of the best chemical rockets. The performance gains were undeniable. Mars missions became feasible. Outer planet exploration became possible within human lifetimes. But between concept and capability lay a vast engineering challenge that would produce some of the most dangerous test failures in the history of the space program. Los Alamos Scientific Laboratory led the reactor development under Project Rover. The first series of test reactors carried the designation Kiwi, named after the flightless bird because these engines would never fly. They were ground test articles, designed to prove the concept and push the technology to its limits. Between 1959 and 1964, Los Alamos conducted multiple Kiwi tests at the Nuclear Rocket Development Station in Area 25 of the Nevada test site. The early Kiwi A series established basic feasibility. Kiwi A Prime ran for 5 minutes in July 1959, reaching 70 megawatts of thermal power. The reactor used uranium dioxide fuel elements clad in niobium carbide, cooled by liquid hydrogen flowing at cryogenic temperatures. The engineering challenges were immediate and profound. Materials that could withstand 2,500 Kelvin temperatures while exposed to hydrogen, intense neutron flux, and thermal cycling simply did not exist. Los Alamos had to invent them. Kiwi B series pushed power levels higher. Kiwi B-1A achieved 900 megawatts in December 1961. Kiwi B-1B reached 1,000 megawatts in September 1962. Each test revealed new failure modes. Fuel elements cracked under thermal stress. Hydrogen leaked through microscopic fissures. Coating materials eroded in the hydrogen flow. The tie tubes that held fuel elements in place vibrated and fractured. Each failure was documented, analyzed, and addressed in the next iteration. But some failures were more severe than others. On September 1, 1962, Kiwi B-1B suffered a catastrophic failure during shutdown. The reactor had been operating successfully when flow instabilities caused fuel elements to eject from the core. Core temperatures spiked. Fuel elements began to disintegrate. The test had to be terminated immediately, but damage was extensive. Radioactive debris contaminated the test cell. The incident revealed fundamental vulnerabilities in the coolant system design that would require complete redesign. The Atomic Energy Commission classified the full extent of the contamination. Internal documents detailed radiation plumes that extended beyond the test site boundaries, but public reports minimized the scope. Off-site monitoring detected elevated radiation levels, but the data remained restricted. The AEC justified the classification on national security grounds. The Soviet Union was developing its own nuclear rocket program, and any indication of American technical difficulties could be exploited. Kiwi B-4A in November 1962 demonstrated improved fuel element design, but KIWI-B4D in May 1964 encountered severe vibration problems that caused fuel element damage. Each test pushed the technology forward while revealing new challenges. The program was making progress, but it was progress measured in controlled failures, in understanding how these machines broke before they could be made reliable. And then came Kiwi TNT. The transient nuclear test was conceived as a deliberate destructive test. Engineers needed to understand the worst-case failure mode, a rapid, uncontrolled power excursion. What happens when a nuclear rocket reactor goes prompt critical? How does the core disassemble? What are the consequences for surrounding systems, for personnel, for contamination? On January 12, 1965, they found out. Kiwi TNT used a modified Kiwi B4 reactor with the control drums locked in the most reactive position. The test plan called for rapid insertion of reactivity by withdrawing the control rods far faster than any operational scenario would allow. The goal was to achieve a nuclear excursion that would destroy the core, and the reactor went from shutdown to prompt critical in less than a second. Power levels spiked to approximately 4,000 megawatts in 35 milliseconds. The fuel elements vaporized. The core structure failed. The reactor vessel ruptured. Hydrogen in the system ignited, producing a fireball visible from miles away. Radioactive fuel fragments were ejected across the test area. Some pieces traveled over 100 feet from the test pad. The explosion was not nuclear in the sense of a fission weapon. This was a thermal and mechanical disassembly caused by the rapid energy release vaporizing the core materials. But the radiological consequences were severe. The test site was heavily contaminated. Cleanup operations would continue for months, and the Atomic Energy Commission immediately classified the detailed results. What became public was minimal. A test was conducted, the reactor was deliberately destroyed, data was collected. What remained classified was the specifics of the fuel ejection patterns, the downwind contamination plume, the radiation exposure levels at various distances, and the implications for reactor safety in operational scenarios. Internal AEC documents reveal the concern. If a NERVA engine suffered a similar excursion during launch or in flight, the consequences would be catastrophic. A launch pad failure would contaminate the Cape Canaveral area. An in-flight failure during ascent would spread radioactive debris across a wide area. An excursion in orbit would create long-lived radioactive debris. The Kiwi TNT data was essential for understanding these risks, but it was data the AEC had no intention of sharing publicly. The nuclear rocket program continued. NERVA NRXA-2, tested in September 1964, had already demonstrated 1,100 megawatts and specific impulse of 825 seconds. NRXA-3, in April 1965, reached 1,180 megawatts. These were not small experimental reactors. These were full-scale nuclear rocket engines producing thrust levels comparable to the J-2 engines used on the Saturn V upper stages. But accidents continued to plague the program. Hydrogen fires were a persistent hazard. Liquid hydrogen at 20 Kelvin leaked from seals, valves, and connection points. In contact with air, it formed explosive mixtures. Any ignition source, a static spark, a hot surface, would ignite it. The flames were nearly invisible in daylight, making them extraordinarily dangerous for personnel. Multiple fires occurred during test operations, some minor, and some requiring evacuation of the test area. Fuel element cracking remained a fundamental challenge. The thermal gradients were extreme. The outer surface of a fuel element might be at 2,700 Kelvin, while the interior was 600 degrees cooler. The uranium carbide fuel expanded and contracted. The niobium carbide coating had different thermal expansion properties. Cracks were inevitable. And cracks meant two things: loss of structural integrity and release of fission products into the hydrogen exhaust. Every NERVA test released radioactive materials. This was inherent to the design. Fission products generated in the fuel were carried out with the hydrogen exhaust. Krypton, xenon, iodine isotopes all were vented directly into the atmosphere during ground tests. The test site had extensive monitoring systems to track the plumes, but the data was classified. Off-site populations received radiation doses from these tests, but the AEC maintained that levels were within acceptable limits. Acceptable by whose standards? By what criteria? these questions were not openly debated. NRXEST, in March 1966, was the first engine test in a simulated space environment, conducted in a massive vacuum chamber. The test revealed new problems with reactor startup in vacuum conditions. Phoebus 1A in June 1965 achieved 1,090 megawatts. Phoebus 1B in February 1967 reached 1,500 megawatts, the highest power level ever achieved by a nuclear rocket. Phoebus 2A in June 1968 pushed to 4,000 megawatts, demonstrating that scaling to larger engines was feasible. But each success came with classified failures. Fuel elements continued to crack. Hydrogen leaks persisted. Vibration issues damaged internal components. And the contamination problem was never solved. Each test left the test stand heavily radioactive. Maintenance required remote handling equipment. Components could not be reused. The entire infrastructure was becoming a radioactive liability. By 1970, the program had conducted multiple successful full-duration tests. NERVA XE Prime, in March 1969, completed 28 starts and accumulated 115 minutes of operation, including a full-duration burn at flight power levels. The technology worked. A nuclear rocket engine could be built, could be operated, could deliver the performance needed for Mars missions. But the political and environmental context had shifted. The Apollo program was winding down. Mars missions were no longer a national priority. The cost of continuing NERVA development was substantial, and the benefits were abstract. The environmental movement was gaining strength, and the idea of launching nuclear reactors into space was increasingly controversial. The Atomic Energy Commission was under pressure to reduce atmospheric testing and limit radiation releases. And there were the accidents that could not be hidden. In August 1969, during preparations for a Phoebus test, a hydrogen leak led to a fire that damaged test equipment and delayed operations. In February 1970, during NRX-A6 disassembly, a fuel element handling accident released contamination in the maintenance area. These incidents were reported internally but not publicized. The AEC maintained strict control over information related to nuclear rocket testing. The final NERVA test occurred in December 1972. By then, the program was already being terminated. In January 1973, President Nixon announced the cancellation of NERVA as part of broader cuts to NASA's budget. The official reason was cost. The unstated reason was that nuclear rockets had no mission. Without a commitment to Mars exploration, there was no justification for the expense and risk. The test facilities at Jackass Flats were decommissioned. The reactors were disassembled and buried. The test stands were decontaminated as much as possible and then abandoned. The site remains contaminated to this day. Area 25 of the Nevada test site is closed to public access. The soil contains plutonium, uranium, and fission products from 14 years of nuclear rocket testing. The Atomic Energy Commission classified the full scope of the contamination, so documents detailing off-site radiation exposure were restricted. Data on fuel ejection from the Kiwi TNT test remained classified for decades. Information about hydrogen fires, fuel cracking, and coolant failures was minimized in public reports. The narrative presented to the public was one of technical success, terminated by budget constraints. The reality was more complex. Project Rover demonstrated that nuclear thermal rockets could work. The specific impulse was real. The thrust levels were achievable. Mars missions were feasible with NERVA technology. But the program also demonstrated that these engines were extraordinarily dangerous to test, difficult to maintain, and impossible to operate without releasing radioactive materials. Every solution created new problems. Every advance revealed new failure modes. The tragedy is not that the technology failed. The tragedy is that we developed a technology we were not mature enough to use safely. We built engines that could take us to Mars, but could not be tested without contaminating the desert. We achieved performance levels that made interplanetary travel practical, but could not solve the fundamental problem of cracking fuel elements. We proved the concept, but could not accept the consequences. Today, the NERVA test data remains partially classified. The full details of the Kiwi TNT explosion are still restricted. The contamination maps for the test site are not public. Radiation exposure data for off-site populations has never been fully disclosed. The Atomic Energy Commission and its successor agencies maintain that classification was necessary for national security. But national security is often a convenient justification for avoiding uncomfortable questions. What were the actual radiation doses received by populations downwind of the test site? How many fuel element failures occurred across the test program? What were the failure rates for critical components? How much radioactive material was released into the atmosphere during 14 years of testing? These are not hypothetical questions. The data exists. It simply remains classified. The dream of nuclear rockets has not died. NASA periodically revisits the concept. New designs promise to solve the old problems. Modern materials, better engineering, improved safety systems. But the fundamental challenges remain unchanged. A nuclear thermal rocket must operate at extreme temperatures, must handle liquid hydrogen, it must withstand neutron bombardment, and must do all of this without releasing unacceptable amounts of radioactive material. Project Rover proved it could be done. It also proved the cost. Not the financial cost, though that was substantial. The cost in contaminated land, in radiation exposure, in accidents classified and forgotten. The cost of pushing technology faster than wisdom. The test stands at Jackass Flats still stand, slowly decaying in the desert sun. The concrete is cracked. The steel is rusted. The radiation monitors are long silent. But the contamination remains, a permanent legacy of 14 years of nuclear ambition. We built engines that could have taken us to Mars. Instead, they took us to the limits of what we were willing to sacrifice for progress. And when we reached those limits, we classified the evidence and walked away. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.
Hey, so today we're finally doing the deep dive into nuclear thermal propulsion that you've all been asking about. And look, if you've played Kerbal Space Program, you know these engines. They're amazing. But here's the thing that blows my mind. A lot of people think nuclear rockets are pure science fiction. They're not. We actually built and tested these things. We just never launched them. Let me take you back to 1962. Kennedy's standing before Congress, basically saying, hey, give us money so we can go to the moon and maybe win this space race thing. But here's what most people forget. The moon wasn't the only thing on his list. Additionally, $23 million combined with $7 million already allocated will accelerate development of the rover nuclear rocket. He asked for communication satellites, weather satellites. We got all of those. The nuclear engines, they got built, they got tested, they just never flew. And it wasn't because of some impossible physics problem or engineering nightmare. Nope. Politics killed it. The Nixon administration rolled around in the early 70s and basically said, we're not doing another giant space thing. So they axed the technology that would have gotten us to Mars. Just like that. There was a little comeback in the 80s. Some Strategic Defense Initiative research brought it back briefly. But then, silence. For decades. But now things are getting interesting again. There's this mission called Draco, demonstration rocket for agile cislunar operations, and it's supposed to fly to high Earth orbit before the decade's out. Actually fire up a nuclear thermal engine in space. So yeah, I want to walk you through what these engines actually are, why they're better than regular rockets in some ways, and what problems we still need to solve. Okay, so the first real concept for a nuclear rocket came from Val Cleaver and Leslie Shepard back in 1948. They published these papers through the British Interplanetary Society, laying out the basics. And this was when reactors were mostly just for research or making plutonium for bombs. Pretty wild timing. Here's how nuclear thermal rockets work at the most basic level. You've got a nuclear reactor. It heats up propellant. That propellant shoots out a nozzle and pushes you forward. Simple enough, right? Chemical rockets do something similar, except instead of nuclear heat, you're getting heat from a chemical reaction. And at the atomic scale, chemical energy is really just electrons doing their thing, jumping around between atoms, electromagnetic force stuff. All of chemistry basically comes down to electron clouds interacting. Now, don't get me wrong. Chemical engines can be absolutely incredible. But there's a ceiling on how much specific impulse you can squeeze out of a chemical reaction. The best thing we commonly use is hydrogen and oxygen. Sure, on paper, hydrogen and fluorine would be a bit better, but you're taking on a ton of extra risk for not much payoff. Fluorine is nasty stuff. Nuclear energy, though? That's protons and neutrons in the nucleus interacting through the strong nuclear force. Way more powerful. That's why nuclear reactions release so much more energy than chemical ones. But wait, that only explains why nuclear bombs are more powerful than chemical explosives. Doesn't really tell us why nuclear rocket engines are better, does it? So here's the deal. Two things define rocket engine performance: how much thrust you get, and how efficiently you generate that thrust. Specific impulse. You've probably heard of ion thrusters. They get like 10 times the specific impulse of chemical engines. Super efficient, but they need tons of electrical power and produce almost no thrust. Nuclear thermal engines, they're kind of in a sweet spot. About twice the specific impulse of chemical engines, but with real thrust, comparable to an upper stage engine. Not enough to lift off from Earth. You still need chemical rockets for that. But once you're in space, you can make big moves fast and use half the propellant. That's huge. Both chemical and nuclear engines work by pushing hot gas through a nozzle. What you want is the fastest possible particles in that gas. And without boring you with kinetic theory derivations, particle speed depends on the square root of temperature divided by molecular mass. So, hotter exhaust, GEER, more efficient. Lighter molecules, GEER, more efficient. Here's where it gets interesting. For temperature, chemical engines actually win this round. The combustion chamber in an RS-25 burning hydrogen and oxygen hits about 3,300 Kelvin. That's hot enough to vaporize iron. So hot the chamber walls would literally disintegrate if we weren't constantly pumping liquid hydrogen through them to keep things cool. In a nuclear rocket, the hydrogen comes in cold and picks up heat from the reactor core. But thermodynamics says heat only flows from hot to cold, so the core has to be hotter than your exhaust. And there's a limit. Get too hot, and the core starts melting. In 0G, there's no down, so instead of a meltdown, you get a very exciting engine-rich exhaust situation. Not ideal. The tested nuclear engines got their exhaust to about 2,300 Kelvin. A full 1,000 degrees cooler than chemical exhaust. So how do nuclear engines win? Molecular mass. The RS-25 burns hydrogen and oxygen, which makes water. Water has a molecular mass of 18. In nuclear thermal engines, hydrogen just passes straight through, hopefully without any chemical reactions, and comes out the other end. Molecular mass of 2. That's 9 times better, which translates to about 3 times better in the velocity equation. That's a massive advantage. All right, theory's great. Let's talk about how you actually build one of these things. Picture the NERVA engine. In the middle, you've got the reactor core. Down at the bottom, the nozzle where gas comes out. You can see some pipes running around. One carries liquid hydrogen down around the casing, nozzle, and throat. Keeps everything cool. But as it does that, the hydrogen heats up and becomes a gas. That gas goes back up through another pipe and hits a turbine at the top. The turbine drives a pump that pushes more hydrogen from the tank through the reactor core. After leaving the turbines, the gas goes through 2 little steerable nozzles that handle roll control. You'll also notice high-pressure helium cylinders for pressurizing the hydrogen tank, and these rod-like things that control whether the reactor goes critical or not. Regular reactors on Earth use control rods that go through the core. Space reactors? They use control drums. Half the drum absorbs neutrons, half reflects them back in. Twist these around and you control the neutron balance in the core. Neutrons escaping? No criticality. Neutrons bouncing back in? Now you're cooking. If you saw my Snap 10 episode, same basic idea. Now let's talk about the core itself. This thing had to be completely different from anything we'd built before. In space, mass is everything. The core needs to be compact enough for a rocket, gas-cooled in a way that transfers heat crazy fast, and designed for way higher temperatures than normal reactors. Your typical power reactor might run around 1000 Celsius. A nuclear rocket, more like 2000 or higher, and it has to handle the full range from liquid hydrogen temperatures all the way up to 2500 degrees. That higher temperature rules out a lot of materials. Some things just get weak at those temperatures. But here's the bigger problem. Hydrogen flowing through the core gets really chemically reactive when it's that hot. Lots of reactors use graphite as a moderator to help with criticality. Graphite handles high temps pretty well. But when you flow 2500-degree hydrogen over graphite, it starts reacting, makes methane. In some early tests, they were literally dissolving the graphite like sugar in hot water. Not great. So they developed special niobium carbide coatings to protect the graphite and keep hydrogen from diffusing through and wrecking everything. Those early reactors used graphite composite fuel rods, hexagonal shapes with channels down the middle for hydrogen to flow through. The graphite contained tiny particles of actual fuel, uranium-235. And yeah. The test reactors used 95% enriched uranium, basically bomb-grade stuff. You can't use straight uranium metal because it melts at around 1/100 Celsius. So you make uranium oxide instead, turn it into tiny grains, clad each grain in graphite, mix it all together, bake it into a rough fuel rod, then machine and coat it into the final fuel element. The hexagonal rods packed together nicely. Tie rods held them together and handled mechanical loads, plus vibration isolation. Turns out when you're pushing hundreds of kilograms of hydrogen through tiny holes, things shake. A lot. Quick note on that 95% enriched uranium. The US has backed away from that for space stuff. Now they're using about 20% enriched. It's called HALEU, high-assay, low-enriched uranium. Technically, 19.75%. You can still make a nice compact reactor with good moderators, and you can get decent lifespan if you breed a little plutonium from the reaction neutrons. Speaking of moderators, I've mentioned them a few times. What they do is slow down neutrons, which makes fission more likely. Think of it like a golf ball rolling past a hole. Going too fast? It'll skip right over, slow it down, and it's more likely to drop in. Graphite's a good moderator, so is hydrogen. And this matters a lot when you're figuring out how to control criticality. You can actually design the reactor so it won't reach full criticality until hydrogen is flowing through. Higher power only kicks in when you've got propellant actively cooling the core. The hydrogen's moderating effect is just one of a million variables. Temperature changes affect the neutron spectrum, which affects reactivity, which affects temperature. You get these weird feedback loops. Starting one of these reactors and getting to full thrust takes a couple minutes. Shutting down isn't instant either. You can close the control drums and stop the fission reactions pretty fast. But while it was running, it was creating fission products. Those are radioactive. They decay. And as they decay, they release heat. So even after you stop the fission, the core keeps producing heat for a while. You've got to keep flowing hydrogen through it, or the whole thing overheats and wrecks itself. This is a huge headache for mission planning. You've got to account for ramp-up and ramp-down times in your trajectory calculations. Other fun complications. The engine can be reused multiple times, but you're burning through fuel each time. So depending on where you are in the engine's life, you might have different thrust levels or different ramp times. And then there's the xenon pit. During fission, you make tellurium, which decays to iodine, which decays to xenon-135. That stuff is one of the best neutron absorbers out there. After you've run the reactor for a while, all that xenon builds up and makes it really hard to restart. Like, you might do a big maneuver and then have to wait 24 hours before you can do anything else because you literally can't get the reactor critical again. But hey, it's not all bad news. If you've got a nuclear reactor up there, you can use it to make electricity. Run a secondary closed-cycle cooling loop through a turbine and generator. Boom, electrical power. You'd probably run the reactor at low power for most of the mission, and only crank it up to multi-gigawatt thermal levels when you need to do big maneuvers. Now let's talk radiation, because yeah, this is a thing. The most powerful reactors ever operated were part of the NERVA rover test programs. They were putting out thermal power around 4 gigawatts. At that level, you're basically exploding 1 ton of TNT every second. So every 10 seconds, that's like a 10-ton nuclear warhead. The Davy Crockett, smallest nuke the US ever deployed, would kill people within 160 meters instantly from radiation alone. That's a lot of neutron radiation coming off these engines. And it's a spacecraft, right? You want it light. You can't just pile on shielding everywhere. So instead, you put the crew or payload at the far end of the propellant tank. Then at the top of the engine, you put a narrow shield that only protects in one direction. Creates a shadow shield, where the lethal radiation doesn't reach during operation. A full fuel tank helps too, but you can't count on that once you've used all your propellant. And remember, even after it stops running, there's still decay radiation from all those fission products. When you're planning missions with nuclear thermal engines, you want to make sure they're not firing within like 100 miles of a space station. When the spacecraft reaches its destination, the payload section carefully detaches, staying inside that radiation shadow, and uses regular chemical thrusters to slowly reach where it needs to go. The highly radioactive nuclear engine just hangs out on its own, like an outcast. Most designs have enough fuel for multiple uses. You'll typically see plans where the engine makes 10 trips to and from the moon, refueling with hydrogen each time, before finally getting disposed of. Every payload coming up has to carefully navigate down that shadow shield corridor and dock. Disposal is interesting too. If it's up in space, it might eventually come back to Earth someday. You want to make sure the radiation has decayed enough by then. With Draco, the plan is to put it in a really high orbit where there's no other spacecraft. When it does engine burns, they'll only be perpendicular to the orbital plane, just changing inclination. It'll never slow itself down and fall back to Earth, or boost out and potentially return some other way. So, yeah, this is real technology. It's almost certainly happening. Used right, it could massively expand what we can do in the solar system. But it's not like Kerbal Space Program. You can't stick these engines right next to your crew and flip them on and off instantly. This is way more complicated than regular rockets. It has its niche. It won't replace chemical engines for liftoff, not enough thrust. Ion thrusters will always have better specific impulse in their domain. Oh, and I should mention, I've only been talking about solid core nuclear thermal engines. There are some wild ideas out there that say, well, if we can't make the core hot enough without it melting, why not let it melt? Liquid cores, even vaporized cores of fissile material undergoing nuclear reactions. The performance would be insane. The engineering challenges would also be insane. There are other propellant options too. I've been focused on hydrogen, but ammonia is another possibility. Liquid ammonia is way easier to store than liquid hydrogen. And yeah, ammonia's heavier, but when you heat it up enough, it breaks apart into hydrogen and nitrogen. You still get great performance without all the liquid hydrogen headaches. I'm excited for this demo in 2027. Not sure when we'll actually see it on a real space mission though. If you want the best specific impulse and you've got plenty of time, like a robotic probe, electric propulsion still wins. Nuclear thermal shines when you don't have time, when you need high thrust and high performance. That usually means crewed missions. But crewed missions with all this radiation around, That adds a whole layer of complications you just don't have with chemical engines. For something like sending people to Mars, mission designers might decide that sticking with chemical engines and just moving more mass into orbit is the simpler path. But as our ambitions grow, as the delta-V requirements keep getting bigger, eventually the rocket equation wins, and nuclear propulsion becomes the answer. Fly safe. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.
December 1972. A remote stretch of Nevada desert. Engineers started a countdown that would change everything and then be erased from history. For 1 hour and 49 minutes, longer than most feature films, an engine screamed with the fury of a captured sun. Inside its core, uranium atoms shattered 93 million times every single second, superheating hydrogen to temperatures that would vaporize diamonds in an instant. The Earth shook, radiation alarms wailed, and the men watching from 2 miles away, sheltered behind concrete and lead, understood exactly what they'd created: a spacecraft engine capable of carrying humans to Mars. This wasn't some crude experiment. The nuclear inferno performed so flawlessly, so predictably, that the monitoring team actually grew restless from the lack of drama. Yet today, this breakthrough collects dust in government warehouses, a phantom in NASA's forgotten files. This is NERVA, the engine that could have put your grandparents on Mars, and the bizarre story of why we chose to pretend it never existed. Every rocket humanity has ever built wages the same futile war against physics. Picture trying to throw a baseball from Earth to the moon using nothing but muscle. It doesn't matter how perfect your form is, your arm simply can't generate enough velocity. That's chemical rockets attempting Mars missions. Beautiful, refined to perfection, but imprisoned by fundamental limits. The Saturn V's legendary J2 engine, the machine that flung Apollo astronauts moonward, achieved 421 seconds of specific impulse. Think of it as your rocket's miles per gallon, measured in thrust seconds per pound of propellant. The Space Shuttle's main engines managed 453 seconds, and that's the ceiling. That's as far as chemistry goes. The molecular bonds in hydrogen and oxygen can only store so much energy, a firecracker compared to what lurks inside atoms. NASA ran the numbers in 1969, and the results were absurd. A chemical Mars expedition would require launching 800 metric tons into orbit, 6 complete Saturn V missions just to make the trip possible. The vehicle would be 85% fuel tanks, 14% structural framework, and just 1% crew compartment. An enormous flying gas station with humans crammed into a closet. But atomic nuclei don't recognize chemical boundaries. Packed inside every gram of uranium-235 weights the energy equivalent of 3 tons of coal. While chemical engines combine liquids and hope for the best, nuclear fission rips apart the very fabric of matter itself. The calculations weren't optimistic projections, they were mathematical certainties. Nuclear thermal rockets promised 825 to 900 seconds of specific impulse, double what any chemical reaction could deliver. Imagine your throwing arm suddenly gaining enough power to reach orbit. So in 1955, while hydrogen bombs turned Pacific atolls into radioactive glass, a top-secret initiative launched in the New Mexico desert. The mission was to harness atomic fire not for destruction, but for exploration. Project Rover emerged from the exact laboratories that birthed the atomic bomb. Los Alamos Scientific Laboratory, staffed by Manhattan Project survivors, joined forces with the United States Air Force. Could humanity ride nuclear flames beyond Earth's atmosphere? Security classifications were so extreme that scientists couldn't explain their work to their own spouses. They simply vanished into the desert for weeks at a time, returning home exhausted, their clothing triggering radiation detectors. On July 1, 1959, humanity crossed an invisible line at Jackass Flats testing ground. The Kiwi A reactor achieved criticality, deliberately named after the flightless bird because this version would never leave the ground. What Kiwi A accomplished had never been done before. It used controlled nuclear fission to heat hydrogen gas and generate thrust. For 5 continuous minutes, 70 megawatts of atomic power, enough electricity for 50,000 households, forced superheated gas through a rocket nozzle. Los Alamos director Norris Bradbury, observing through periscope monitors, made the announcement, "We have unleashed the atom for propulsion." Then Kennedy issued his lunar challenge, and everything shifted into overdrive. Although Kennedy's famous 1961 address focused on defeating the Soviets using conventional technology, NASA Administrator James Webb was thinking decades ahead. In classified briefings to Congress, Webb revealed the actual strategy. The moon is merely a rehearsal. Reaching Mars within our generation requires nuclear propulsion. Nothing else will suffice. Project Rover suddenly received blank check authorization. Build it. Perfect it. Prepare it for flight. The Nevada wasteland transformed into humanity's atomic proving ground. Kiwi B-4E roared to life on August 28, 1964. It operated for 8 minutes at 937 megawatts, approaching 1 gigawatt of raw power. Vibrations traveled so violently that cameras 2 miles distant required special mounting equipment. Werner von Braun, architect of the Saturn V, stood watching in stunned silence. His personal notes recorded, "This engine operated 10 times longer than my F-1 rockets. We are witnessing Mars become achievable." But the true behemoth was Phoebus 2A. On June 26, 1968, engineers released 4,082 megawatts of thermal energy, over 4 gigawatts, matching 4 commercial nuclear power stations combined. For 12 uninterrupted minutes, this reactor sustained temperatures that liquefied steel, contained forces capable of leveling buildings, and performed so smoothly that technicians described the test as unremarkable. Phoebus wasn't merely the mightiest nuclear reactor ever constructed. It proved that atomic rockets had evolved from concept to proven technology. Harold Finger faced an engineering nightmare. As director of space nuclear propulsion, he had to contain 30,000-degree hydrogen, temperatures capable of vaporizing tungsten, inside a reactor designed to fly. His solution sounded like fiction but functioned like precision machinery. Hexagonal fuel rods, each pencil-sized, honeycombed with 19 hair-thin cooling passages. Liquid hydrogen at minus 253 degrees Celsius would surge through these channels, absorbing heat from the uranium core, then explode from the nozzle at speeds that embarrassed chemical engines. The hydrogen served triple duty as propellant, cooling system, and radiation barrier all at once. This wasn't theoretical speculation. Between 1964 and 1969, engineers subjected over 20 distinct fuel element configurations to punishment that would shatter ordinary materials. They heated them to 2,500 degrees, flash-cooled them to near absolute zero, then repeated the cycle. 60 complete thermal oscillations, each a round trip from polar temperatures to stellar core heat. On December 15, 1967, NRXA-6 demonstrated what years of iteration could produce. The engine fired for 62 consecutive minutes, over 1 hour of sustained nuclear thrust. For context, the Saturn V's F-1 engines burned for just 168 seconds total. NERVA ran 22 times longer while holding power output within 1% tolerance. NASA's official technical assessment used uncharacteristically emotional language, unprecedented achievement across all measured parameters. But XE Prime represented the crowning accomplishment. Tested just 3 days after Apollo 11 returned to Earth, this wasn't simply a reactor, it was an integrated propulsion system. Turbopumps cycled. Actuators responded to commands. Flight computers calculated trajectories. On December 11, 1969, XE Prime executed 28 separate restart sequences, scaling from idle 20% capacity to maximum nuclear output and back again. It logged 115 minutes of total operation, proving nuclear rockets weren't just powerful, they were dependable. Program director Milton Klein informed journalists, "XE Prime isn't an experiment. This is operational hardware. We could attach this engine to a launch vehicle tomorrow and depart for Mars. The price tag for this revolution? $1.4 billion across 17 years, less than NASA spent coding the Saturn V rockets. By 1969, with XE Prime humming in the desert, NASA drafted construction plans for nuclear Mars vessels. Not distant fantasies, engineering specifications marked ready for manufacturing. NASA's Integrated Program Plan, delivered to President Nixon on September 15, 1969, wasn't a wish list. It was an operations manual for claiming the solar system. The 500-page document, now buried in archives, specified nuclear space shuttles operational by 1978, a permanent lunar installation by 1980, and American astronauts walking on Mars by November 1982. These timelines assumed existing, tested hardware. The elegance was stunning. Swapping the Saturn V's third stage for a NERVA engine would boost Mars payload capacity from 30 tons to 75 tons. Picture transporting your house in a pickup truck versus an 18-wheeler. That's what NERVA offered. Transit time would compress from 260 days to 180 days, meaning crews would absorb 30% less cosmic radiation, landing in better condition and ready for surface operations. Wernher von Braun became NERVA's most passionate advocate. Standing before Congress in November 1969, the man who sold America on lunar exploration now preached nuclear destiny. Chemical propulsion gives us ceremonial visits to Mars. Nuclear propulsion gives us Martian civilization. His engineering teams conducted 10,000 computer simulations using actual XE prime performance data. The verdict was clear. NERVA could deliver a complete Mars outpost in just 3 launch campaigns. The nuclear shuttle concept pushed even further. These atomic workhorses would remain stationed in orbit, ferrying supplies between Earth and Moon like interplanetary freight haulers. Boeing's analysis showed each shuttle completing 10 round-trip missions before requiring service, slashing lunar resupply expenses by 68%. The Moon would become a refueling depot, and Mars would become a neighboring settlement. Then, on January 5, 1973, a single paragraph from the Office of Management and Budget executed the future. The NERVA program is terminated effective immediately. The justification was bureaucratic savagery. All technical milestones have been achieved or surpassed. The engine is prepared for flight development. However, no missions currently exist requiring this capability. Senator William Proxmire, NERVA's political assassin, delivered the final verdict. We're pouring millions into Mars expeditions while Americans struggle with poverty. The nation that invested $25 billion reaching the Moon couldn't allocate $200 million to complete the engine that would carry us beyond it. NERVA perished not from failure, but from succeeding at the worst possible moment. But atoms are patient, and physics never forgets. Because 5 decades later, the nuclear rocket has emerged from its tomb. And this time, it's not alone. On May 25, 2019, NASA Administrator Jim Bridenstine stood at Marshall Space Flight Center and uttered words that once seemed impossible. NASA is returning to nuclear propulsion. The agency unveiled Draco, the demonstration rocket for agile cislunar operations, targeting a nuclear thermal flight test by 2027. After 50 years of exile, atomic power was reclaiming space. The geopolitical landscape had transformed. In January 2019, China's Chang'e 4 touched down on the Moon's far side, planting their banner where no human eyes could witness, a fitting symbol of their ambitions. Chinese planning documents outlined nuclear cargo vessels servicing lunar colonies by 2035. Russia announced their nuclear-powered space tug in 2018, claiming it would render chemical rockets as outdated as wooden sailing ships. The space race had resumed, a marathon, not a sprint. Lockheed Martin secured the Draco contract in July 2023, partnering with BWX Technologies, the company that builds reactors for America's nuclear submarine fleet. Kirk Shireman, Lockheed's lunar exploration director, offered a surprising confession. We're not pioneering new ground. We're studying homework completed in 1972. NERVA's engineers already solved every challenge we're encountering. The technological resurrection is stunning. Contemporary triso fuel particles, ceramic spheres smaller than poppy seeds, can withstand 1600 degrees Celsius, eliminating NERVA's one weakness, which was gradual fuel degradation. Each microscopic particle functions as its own containment system, wrapped in layers of carbon and silicon carbide. General Atomics' newest reactor design, incorporating these particles, promises 900+ seconds of specific impulse, double any chemical system ever built. Ultra-safe. Nuclear Corporation's Michael Eads captures the absurdity. NERVA engineers wielding slide rules accomplished what we're struggling to replicate with supercomputers. They would cry seeing our materials. Carbide composites that ignore extreme heat. Additive manufacturing, computer modeling. We're not exceeding NERVA's performance. We're trying to match it, which forces us to confront the calculation that haunts aerospace engineers at night. If NERVA had continued evolving for 50 years, where would humanity stand today? The mathematics of squandered potential is devastating. NERVA achieved flight readiness in 1972. With continuous refinement, routine Mars cargo deliveries would have begun by 1990. Permanent Martian settlements housing 1,000 inhabitants were feasible by 2010. Nuclear propulsion makes asteroid mining economically viable. The velocity requirements to reach near-Earth asteroids drop from prohibitive to trivial. We could have been extracting trillion-dollar mineral deposits since the 1990s, spawning entire space-based industries. The International Space Station could have been assembled in 3 years using 8 nuclear shuttle missions. O'Neill cylinders. Those magnificent rotating space habitats transform from science fiction into engineering projects when launch costs collapse by 80%. We could be inhabiting orbital cities today. Here's the cruelest arithmetic. Fusion propulsion, the ultimate interstellar engine, demands massive orbital infrastructure. With nuclear thermal rockets providing affordable access to space, fusion experiments could have progressed in orbit since the 1980s. Today, we might be dispatching probes to neighboring star systems instead of struggling to revisit our own moon. So we're left confronting NERVA's Spectre, a flawless engine that performed too well for its own survival. Somewhere in the Nevada wilderness, test facilities stand like concrete monuments. The rails that once carried NERVA engines have oxidized to rust, yet remain sturdy enough to support another rocket. The control room sits abandoned, populated only by tumbleweeds and echoes. These aren't memorials to defeat. They're memorials to a future we constructed, validated, and perfected, then walked away from. NERVA proved something profound about our species. The obstacles to human expansion aren't technological, they're psychological. We didn't abandon nuclear rockets because they malfunctioned. We abandoned them because they worked, and then we lacked the nerve to use what we'd built. The engine that operated flawlessly for 109 minutes in 1972 could have been pushing spacecraft toward Mars by 1975. Instead, it was disassembled, analyzed, and archived like a postcard from a future we declined to visit. Today, as Draco resurrects this technology, we're not innovating, we're recollecting. The bitter irony is that modern nuclear thermal rockets, despite their supercomputers and miracle materials, are still struggling to equal what engineers achieved with slide rules and determination in the Nevada desert. Stanley Borowski, NERVA's guardian of legacy, offers the definitive summary. Every Mars mission study eventually rediscovers NERVA. The question isn't whether we'll adopt nuclear propulsion. It's whether we'll acknowledge we already perfected what we need. What do you believe would exist today if NERVA had powered our space program for the past 50 years? Would we be exploring Mars, harvesting asteroids, or would we have invented new excuses to abandon our ambitions? And now that nuclear propulsion is being resurrected, will we finally commit to using it, or will we bury it once more? Share your thoughts below, and tell me which forgotten space technology deserves revival next. If you want more stories of futures we discarded, hit subscribe. Until next time, keep looking up. And remember, somewhere in a filing cabinet, the blueprints for our cosmic destiny are waiting. If you enjoyed this story, subscribe for more tales where history, technology, and human ambition collide. Thanks for watching.
Picture this. You're standing in the Mojave Desert, November 1959. A metal cylinder nicknamed Hot Rod sits on a launch platform. Then, bang, bang, bang. 6 explosions in sequence. The cylinder shoots 184 feet into the air, riding shockwaves like a cosmic pogo stick. This wasn't just another rocket test. This was humanity's proof that we could surf nuclear explosions to the stars. The masterminds behind it had a plan that would make Dr. Strangelove blush. Detonate between 800 and 1,000 atomic bombs beneath a massive steel plate to reach Saturn. They called it Project Orion. History remembers it as visionary, a dream murdered by treaties and politics. But declassified documents and the confessions of its own creators reveal something darker. This is the real account of how America's brightest minds almost turned nuclear Armageddon into a travel itinerary. The mathematics seduced them first. In 1955, deep in the classified vaults of Los Alamos, physicist Stanisław Ulam, the same man who'd helped create the hydrogen bomb, scribbled equations that defied belief. Nuclear explosions, he calculated with mathematician Cornelius Everett, could propel a spacecraft with efficiency that made chemical rockets look like firecrackers. By 1958, this fever dream found its prophets. Ted Taylor, a nuclear weapons designer who'd birthed both the smallest and most devastating fission bombs America ever tested, understood atomic fury like a vintner knows wine. He'd created the 50-pound Davy Crockett warhead and the half-megaton super-oralloy bomb. Freeman Dyson, the theoretical physicist from Princeton who'd already unified quantum mechanics, brought academic legitimacy. Together at General Atomics in San Diego, they engineered the unthinkable. Picture their design: a massive steel plate, thick as a bank vault door, hanging beneath your spacecraft. Connect it with shock absorbers the size of buildings. Now, every second, toss a nuclear bomb out the back. Boom. The blast slams into the plate. The shock absorbers compress like God's own springs. The ship lurches forward. Repeat 1,000 times. The performance numbers seemed pulled from science fiction. Specific impulse. Think of it as your rocket's miles per gallon would hit 6,000 seconds. Chemical rockets? A pathetic 450. Imagine comparing a Formula One race car to a horse-drawn wagon, then multiply that difference by 10. A single Orion launch could hoist 1,600 tons to orbit. The mighty Saturn V that took us to the moon? It managed 140 tons, less than a tenth. Mars in 4 weeks instead of 9 months. Saturn's moons within a single human lifetime. Alpha Centauri, our nearest star, reachable in 130 years instead of 40,000. But this wasn't fantasy. On that November day in 1959, Hot Rod proved the concept with conventional explosives standing in for atomic bombs. 6 sequential blasts, 184 feet of altitude. The physics worked. The engineering was sound. So why aren't we commuting to Jupiter on nuclear explosions today? The answer came from Freeman Dyson himself, delivered in a calculation that would haunt him forever. In 1959, as Hot Rod validated their dreams, Dyson ran the numbers nobody wanted to see. Each Orion launch from Earth's surface would kill between 0.1 and 1 person worldwide from radioactive fallout. Let that sink in. Every single launch, a statistical death sentence for someone somewhere. Think of it this way. You're planning a trip to Mars. Before you leave, you spin a globe, close your eyes, and throw a dart. Wherever it lands, maybe a farmer in Nebraska, perhaps a child in Mumbai, that person dies of cancer so you can ride nuclear explosions to space. Would you still go? Dyson later explained their Cold War logic with chilling honesty. We were comparing this with nuclear war, where hundreds of megatons would kill billions. By those standards, a few statistical deaths seemed acceptable. But here's what those sanitized statistics really meant. Each ground launch required 800 to 1,000 nuclear detonations in rapid sequence, starting at ground level. Imagine setting off the entire Cold War nuclear testing program, concentrated in one spot in under 10 minutes. The radioactive cocktail wouldn't respect borders. Strontium-90, with its 29-year half-life, would settle into soil and accumulate in bones. Cesium-137 would contaminate crops for decades. Iodine-131 would concentrate in milk, targeting children's thyroids. The same isotopes that had driven mothers to protest atmospheric testing would rain down with every launch. Picture the milk recalls of the 1960s. Thousands of gallons dumped because of fallout from distant nuclear tests. Now multiply that by weekly Orion launches. Every glass of milk, every slice of bread, every breath of air becomes a game of radioactive roulette. By late 1959, this realization shattered Dyson's enthusiasm. The man who'd provided Orion's theoretical foundation now saw it clearly. They were planning to poison the planet one launch at a time. He considered even one death too high a price for reaching the stars. Therefore, the same year they proved Orion could fly, its chief theorist began backing away. Not because it wouldn't work, but because it would work exactly as designed, seeding death with every journey skyward. But fallout was just the appetizer to Orion's feast of horrors. The main course: mass-producing nuclear weapons like Model T Fords. Each pulse unit, Orion's euphemism for its propulsion bombs, was essentially a tactical nuclear weapon optimized for thrust. The spacecraft needed thousands. Think about that infrastructure. Assembly lines churning out atomic bombs with the efficiency of a Toyota factory. Warehouses stacked with enough nuclear devices to end civilization. Transport convoys moving nuclear weapons like Amazon packages. Imagine the proliferation nightmare. Any nation that developed Orion technology wouldn't just have a spacecraft. They'd have perfected industrial-scale nuclear weapon production. The specialized bomb designs for propulsion? With minor tweaks, they'd make devastating weapons. It's like developing a revolutionary new car engine that accidentally teaches you to build tanks. In March 1961, the danger became so clear that Vice President Lyndon Johnson personally seized every copy of the Gardner Committee report that had endorsed nuclear propulsion. He locked them in his personal safe, like they were nuclear secrets, because they essentially were. The report had revealed how Orion would hand any ambitious nation the keys to nuclear supremacy. Even the Air Force, not known for turning down powerful weapons, concluded Orion had no military value. But they'd missed the real threat. Orion itself wasn't the weapon. Orion was the excuse to normalize nuclear explosions, to make atomic bombs as routine as rocket fuel. Consider the precedent. If America starts launching spacecraft with nuclear explosions, how does it tell Iran they can't? If peaceful nuclear explosions become acceptable, where's the line? Today, it's spacecraft. Tomorrow, it's excavation. Next week, someone's using nukes to mine asteroids, or to hold the world hostage from orbit. Therefore, Orion represented a Pandora's box that, once opened, would transform nuclear weapons from civilization-ending deterrents into everyday tools, a normalization that could never be reversed. Even if we swallowed the fallout, even if we ignored proliferation, there remained a problem that would make any engineer's blood freeze: controlling a barely contained nuclear chain reaction while riding it to space. The pusher plate, Orion's signature innovation, had to endure hell itself. Each nuclear blast would hit it with temperatures of 67,000 degrees Celsius. That's 11 times hotter than the surface of the sun, delivered in microseconds. The proposed solution: slather the plate with graphite grease between blasts, like you're buttering toast between hammer strikes from Thor. Tests with conventional explosives showed promise. But nuclear explosions play by different rules. Neutron bombardment would transmute the steel itself, making it brittle in unpredictable ways. One microscopic crack, one fatigue fracture invisible to inspection, and the next blast vaporizes your spacecraft. along with the 800 unexploded nuclear weapons still in the magazine. But here's the nightmare that kept even Orion's advocates awake: launch failure. Unlike chemical rockets that burn fuel as they rise, Orion would carry its entire nuclear arsenal from the ground. Picture this. You're 3 minutes into launch. 500 nuclear bombs already detonated. 500 more waiting. A shock absorber fails. The spacecraft tumbles. What happens to those 500 unexploded nuclear weapons when they hit the ground at supersonic speed? Best case, they scatter like radioactive confetti across hundreds of square miles. Worst case, sympathetic detonations create a nuclear groundburst orders of magnitude worse than any bombing in history. There's no abort system. You can't recall nuclear bombs mid-flight like you'd cut a rocket engine. Ted Taylor, Orion's driving force, would later confess, "We were captivated by technical sweetness. The whole thing had gone out of control. Massive. And very scary." Even success meant gambling with catastrophe. Statistical models showed that over multiple launches, catastrophic failure wasn't just possible, it was mathematically inevitable. Launch Orion 10 times, and you're playing nuclear Russian roulette with a partially loaded gun. Launch it 100 times for Mars colonization, you've guaranteed apocalypse. But perhaps Orion's most revealing failure wasn't in its engineering. It was in the minds that created it. To truly understand Project Orion's danger, we must examine the psychology of its creators, brilliant minds drunk on the wine of their own genius. Ted Taylor spent the 1950s at Los Alamos designing instruments of annihilation. During his daughter's birth in 1950, while his wife labored, Taylor sat in the waiting room drawing blast radius circles on maps of Moscow, frustrated that even his 500 kiloton super Oralloy bomb couldn't erase the entire city. He later recalled feeling possessive about his weapons. "My SOB, super Oralloy bomb, my bomb." This was a man who saw nuclear explosions not as humanity's darkest achievement, but as tools in his workshop. Freeman Dyson brought Princeton's prestige to this atomic fever dream, taking sabbatical to work on Orion. Years later, he'd admit, "We were all optimists. Sure, we could make it work." They ignored the uncontrollable, the unpredictable, the fundamentally chaotic nature of writing nuclear explosions. This wasn't isolated madness. It was systemic. The same era that birthed Orion also produced Project Plowshare, which proposed using nuclear bombs to dig canals, extract oil, and reshape continents. Edward Teller, father of the hydrogen bomb, wanted to nuke Alaska to create an artificial harbor. These weren't fringe ideas from crackpots. These were serious proposals from civilization's brightest minds. The atomic priesthood had developed its own morality, divorced from human consequence. In their equations, a statistical death was just a variable to minimize. Radioactive contamination became an acceptable trade-off. They'd become so intoxicated with solving technical problems, they'd forgotten to ask whether the problems should be solved at all. Years later, Taylor would write about his changes of heart, describing the slow realization of what he'd helped create. Dyson would call Orion the greatest moral failure of his career. But in 1958, that wisdom hadn't arrived. They were brilliant children playing with nuclear fire, convinced they could control the flames. Therefore, Orion represented peak atomic age hubris, genius minds so entranced by elegant equations and technical beauty that they nearly normalized the routine detonation of nuclear weapons as humanity's taxi service to the stars. On August 5, 1963, humanity collectively came to its senses. In Moscow, the United States, Soviet Union, and United Kingdom signed the Partial Test Ban Treaty, prohibiting all nuclear explosions in the atmosphere, outer space, and underwater. With the stroke of a pen, Project Orion became illegal under international law. The treaty's preamble reads like civilization's moment of clarity. seeking to achieve the discontinuance of all test explosions of nuclear weapons for all time, to put an end to the contamination of man's environment by radioactive substances. Within 2 years of the treaty's ratification, Project Orion was officially canceled. Freeman Dyson would later lament this as the first time in modern history that a major expansion of human technology has been suppressed for political reasons. Suppressed or saved? Consider what the treaty prevented. A world where nuclear explosions became routine, where every spacefaring nation needed thousands of atomic bombs, where radioactive fallout was the price of progress, where one engineering failure could destroy a continent. George Dyson's definitive history reveals that his father Freeman had already turned against Orion by 1959, convinced that even one cancer death was too high a price. The treaty didn't kill a dream. It prevented a nightmare. The ban forced us to find better ways. Chemical rockets took us to the moon without poisoning Earth. Ion drives now push our probes to the outer planets without splitting atoms in our atmosphere. We learned to reach for the stars without standing on a pile of nuclear corpses. Project Orion fascinates because it almost happened. The physics worked. The engineering was achievable. Hot Rod proved that nuclear pulse propulsion was more than theoretical. It was terrifyingly practical. We stood at the crossroads and nearly took the path to atomic hell. That's precisely what makes it instructive. Orion proves that humanity's most dangerous ideas aren't the impossible ones. They're the brilliant ones we're wise enough to abandon. As Ted Taylor learned through painful experience, there's a disease in nuclear fascination, a technical sweetness that can blind genius minds to monstrous consequences. Today, as we stand on new technological precipices, artificial intelligence that could outsmart us, genetic engineering that could redefine us, geoengineering that could break our planet's climate, Orion's lesson burns bright. Not every problem should be solved with the biggest hammer available. Not every capability should be pursued just because it's possible. The partial test ban treaty didn't steal our cosmic destiny. It proved we'd finally grown up enough to deserve one. By learning to reach space without nuclear explosions, we demonstrated that intelligence means more than solving equations. It means knowing which equations should stay unsolved. Sometimes the greatest achievement of human wisdom isn't what we choose to build, but what we choose to leave buried in the filing cabinets of history. What technology today will future generations view with the same horror we now view Project Orion? Are we pursuing our own Project Orions? Brilliant but terrible ideas we're too entranced to abandon? Comment below with your thoughts. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.
In December 1968, somewhere in the Nevada desert, engineers fired up an engine that would change everything. But when they shut it down, the entire test stand had become so radioactive that they had to control robots from bunkers just to examine it. This was NERVA, the nuclear engine for rocket vehicle application, and it worked. The technology was real, the tests were successful, and according to the plans on the drawing boards, it would put humans on Mars before the end of the century. But there was a problem that no amount of engineering could solve. Every single launch would release radioactive material into Earth's atmosphere. The scientists building it knew it. The politicians funding it knew it. And yet, for more than a decade, the program continued. This is the story of how America's brightest minds, seduced by the promise of nuclear propulsion, built a rocket engine that could have transformed humanity into an interplanetary species. And the moment when we collectively decided that some prices are too high to pay, even for Mars. To understand why NERVA was so revolutionary, you need to understand the fundamental problem with getting to space. Chemical rockets are pathetically inefficient. They work by essentially lighting controlled explosions beneath you and riding the blast, burning through enormous quantities of fuel, for relatively modest velocity gains. It's like trying to cross an ocean by throwing rocks backward from your boat. Technically, it works, but you're going to need a lot of rocks. For decades, this inefficiency was simply accepted as the price of spaceflight. Then, in 1955, something changed. Scientists realized that if you could heat propellant using a nuclear reactor instead of chemical combustion, you could achieve performance that made conventional rockets look like antiques. The concept was elegantly simple. Use a nuclear reactor to heat hydrogen to extreme temperatures, then expel it through a nozzle for thrust. No combustion required, just pure nuclear heat converted directly into velocity. The promise was intoxicating. While the search for specific performance numbers continues, what we know for certain is that nuclear thermal propulsion represented a quantum leap beyond anything chemical rockets could achieve. The difference wasn't incremental, it was revolutionary. It meant the difference between reaching Mars in months versus years. It meant larger payloads, longer missions, and destinations that had previously been pure fantasy. For the engineers working on the problem, nuclear propulsion wasn't just an advantage, it was destiny. In 1960, NASA established the Space Nuclear Propulsion Office with Harold Finger as its first director. Finger was a true believer, convinced that nuclear propulsion was humanity's inevitable future. His challenge was formidable, convincing a skeptical Congress and an anxious public that putting nuclear reactors in space wasn't just safe, but necessary for American supremacy in the Cold War space race. The Soviets had beaten America to orbit with Sputnik in 1957, beaten them to putting a human in space with Gagarin in 1961. The space race wasn't about science. It was about proving which system, capitalism or communism, represented humanity's future. And in that context, nuclear propulsion looked like the ultimate trump card. The program that would become NERVA actually began in 1955 under Project Rover, a joint effort between the Atomic Energy Commission and NASA to develop nuclear thermal rocket engines. Between 1959 and 1962, researchers conducted multiple reactor tests, gradually pushing the boundaries of what was possible. These weren't paper studies or theoretical exercises. They were building real hardware, running real tests, generating real data. The Kiwi A test in 1959 ran for 5 minutes at 70 megawatts of power. Each subsequent test pushed further, ran hotter, lasted longer. The technology was maturing rapidly, but NERVA wasn't the only nuclear propulsion dream being pursued in those heady days of the early space age. Across the country, an even more audacious project was underway, one that made NERVA look conservative by comparison. It was called Project Orion, and its concept was breathtaking in its simplicity and terrifying in its implications. Instead of using a nuclear reactor to heat propellant, Orion would detonate actual nuclear bombs behind a spacecraft and ride the shockwaves. Small nuclear explosives would be ejected from the rear of the vehicle, detonated at a precise distance, and the blast would strike a massive shock-absorbing plate, propelling the spacecraft forward. Then another bomb, and another, each pulse equivalent to multiple Hiroshima bombs. Hundreds of detonations just to reach orbit, thousands for an interstellar journey. The physics actually worked. The engineering team, led by physicist Freeman Dyson among others, calculated that an Orion spacecraft could reach Alpha Centauri within a human lifetime. They even built a small-scale test vehicle and flew it using conventional explosives, proving the concept wasn't just theoretical madness. The spacecraft would be built around the pusher plate, a massive shock-absorbing surface designed to withstand repeated nuclear detonations. The plate would be coated with graphite grease that would ablate with each blast, carrying away heat and protecting the structure. Behind it, enormous shock absorbers would compress and expand, converting the violence of nuclear explosions into smooth acceleration. It was engineering at its most audacious, turning the most destructive force humanity had ever created into a means of transportation. But the terrible realization was unavoidable. Orion would require hundreds of nuclear detonations in Earth's atmosphere just to reach orbit. Each detonation would release radioactive fallout. The cumulative effect would be catastrophic. And when the Partial Test Ban Treaty was signed in 1963, prohibiting nuclear explosions in the atmosphere, underwater, and in space, Project Orion's fate was sealed. You couldn't launch it without violating international law and poisoning the planet. The project was quietly discontinued, a victim of its own ambition. NERVA, by comparison, seemed almost responsible. It wouldn't require atmospheric nuclear detonations. The reactor would only reach full power in the vacuum of space. It could theoretically launch from orbit, assembled by conventional rockets, then ignite safely above the atmosphere. It was nuclear propulsion with a human face, ambitious but not insane. And so, while Orion died, NERVA lived on, attracting funding, political support, and the dreams of visionaries who saw it as humanity's ticket to the solar system. No one championed NERVA more enthusiastically than Wernher von Braun, the German rocket engineer who had designed the V-2 for Nazi Germany and then became the architect of America's space program. Von Braun was a showman, a salesman, a man who could make Congress believe in the impossible. And in 1969, fresh from the triumph of Apollo 11's moon landing, he unveiled his vision for Mars. It was spectacular. A fleet of NERVA-powered spacecraft would launch from Earth orbit, their nuclear engines glowing as they accelerated toward the red planet. The journey would take just months, not the years required by chemical propulsion. Crew compartments would be spacious, with room for laboratories, living quarters, everything needed for the long voyage. They would arrive at Mars, establish a base, conduct exploration, then return home as heroes. Von Braun had the timeline mapped out. With continued funding, humans could walk on Mars by 1982. The technical foundation was solid. By 1968, NERVA engines had completed over 17 tests. They had run for cumulative hours at temperatures that would melt steel. The program had demonstrated that nuclear thermal propulsion wasn't science fiction, it was engineering reality. Milton Klein, the manager overseeing the program for the Atomic Energy Commission and NASA, became its political warrior, fighting budget cuts and public skepticism, arguing that NERVA represented America's best chance to maintain space superiority. The pieces were falling into place. The technology worked. The mission architecture was designed. The political will existed, at least among space advocates. Mars was within reach, not as a distant dream, but as a concrete goal with a concrete timeline. All the ingredients were there for humanity's greatest adventure, except one. Behind closed doors, other calculations were being made. Calculations about fallout patterns, atmospheric dispersion, and statistical casualties. Because while NERVA didn't require nuclear detonations, it wasn't clean. It couldn't be clean. The very physics that made it revolutionary also made it dangerous. The problem was inherent to the design. A NERVA engine worked by pumping liquid hydrogen through a nuclear reactor core heated to extreme temperatures. The superheated hydrogen would then be expelled through a nozzle, generating thrust. But inside that reactor core, neutrons were flying everywhere, and some of those neutrons would inevitably strike hydrogen atoms, transmuting them into radioactive isotopes. Not much, just a tiny fraction of the total propellant. But when you're expelling tons of hydrogen per second, even a tiny fraction adds up. And that radioactive hydrogen wouldn't just disappear, it would be expelled into the upper atmosphere where it would gradually spread across the entire planet, eventually settling back to Earth's surface. Everywhere, diluted, dispersed, but present and radioactive. The health physicists did the calculations. They modeled the dispersion patterns. They estimated the dose rates, and they arrived at a number that would haunt the program. Each NERVA-powered launch would kill between 0.1 and 1 person worldwide from radioactive fallout. Not immediately, not visibly, just a statistical increase in cancer rates across the global population, an invisible toll paid in incremental risk spread across billions of people. One launch might cause one additional cancer death somewhere on Earth. Maybe in Tokyo, maybe in Paris, maybe in a small village in Kenya. The victim would never know. The engineers would never know. it would be completely untraceable, lost in the statistical noise of background cancer rates. This was the moral paradox at the heart of NERVA. The deaths were real but abstract, certain but unidentifiable. It was a trolley problem at cosmic scale. Do you pull the lever to divert the train toward Mars, knowing that doing so will definitely kill someone, even though you'll never know who? The engineers tried to rationalize it. NASA had lost 3 astronauts in the Apollo 1 fire, and the program continued. Test pilots died regularly pushing the boundaries of aviation. Wasn't this just another acceptable risk in the name of progress? Besides, the United States and Soviet Union had already conducted hundreds of atmospheric nuclear tests during the 1950s and early 1960s, each releasing far more radiation than a NERVA launch would the planet was already contaminated. What was one more rocket? But there was a difference, and everyone knew it. Nuclear weapons tests were justified, however tenuously, by national security, by the existential threat of the Cold War. They were presented as necessary evils to prevent something worse. NERVA was different. NERVA was optional. It was about Mars, about exploration, about ambition. And while those goals were noble, were they worth killing for? Could you look at a map of Earth, at the billions of people going about their lives, and say, one of you will die so we can go to Mars faster, and I think that's acceptable? The engineers who had to make these calculations weren't monsters. They were people trying to honestly assess risk, to weigh costs against benefits, to make rational decisions about irrational questions. Some argued that the risk was negligible compared to other hazards humanity routinely accepted: car accidents, industrial pollution, natural disasters. Others felt a creeping horror at what they were contemplating. How do you tell your colleagues that their life's work, the project they've dedicated years to perfecting, will inevitably kill someone? How do you continue working when you know that? The debates happened in conference rooms and internal memos, hidden from public view, because the public conversation was still about Mars, about American supremacy, about the glorious future of space exploration. But privately, the moral foundation was crumbling. The very thing that made NERVA revolutionary, its nuclear power, made it ethically untenable. You couldn't have one without the other. There was no engineering solution to a moral problem, and the context was shifting. NERVA existed within the larger framework of the Cold War nuclear arms race, and by the early 1970s, that framework was changing. The Partial Test Ban Treaty of 1963 had already pushed nuclear testing underground, reflecting growing international consensus that atmospheric nuclear operations were unacceptable. Détente was replacing confrontation. Arms control was becoming politically popular. The Apollo program's success had paradoxically undermined NERVA's case. America had already won the space race using chemical rockets, so why risk nuclear ones? There was also the dual-use problem. The same technology that powered NERVA could be weaponized. A nuclear thermal rocket engine could, with modifications, become a weapon delivery system. If America deployed NERVA, the Soviets would feel compelled to develop their own nuclear propulsion program, escalating the arms race into space. Every advance in space nuclear technology was an advance in weapons technology. The dream of peaceful nuclear propulsion was naive. You couldn't separate the rocket from the reactor, and you couldn't separate the reactor from the bomb. By 1972, NERVA had survived every technical challenge. The engines worked. The tests succeeded. The engineering problems were solved. But the program couldn't survive politics, public opinion, and the growing realization that some technologies are too dangerous to deploy, no matter how well they work. In January 1973, President Nixon's budget eliminated all funding for NERVA. The official reason was budget cuts in the post-Apollo era. Space exploration was expensive, public interest was waning, and there were pressing problems on Earth that needed attention. The unofficial reasons were more complex: environmental concerns, proliferation fears, shifting political priorities, and the uncomfortable moral calculus that no one wanted to defend publicly. The cancellation was swift and final. Test facilities were mothballed. Teams were disbanded. Decades of research were archived. The institutional knowledge that had been so carefully built, the engineers who knew how to safely operate nuclear reactors and rocket engines, the technicians who understood the systems, the managers who could navigate the bureaucracy, all of it scattered. Harold Finger and Milton Klein, the program's champions, watched their life's work disappear. One can only imagine their feelings. Disappointment, certainly. Frustration at what might have been. But perhaps also relief? The moral burden lifted? We'll never know. The speculative alternate timeline is tantalizing and terrifying in equal measure. If NERVA had continued, we might have had permanent Mars bases by the 1990s. The solar system might be humanity's backyard, with routine flights to the outer planets, asteroid mining operations, perhaps even interstellar probes. We would be a different species, defined not by our confinement to one planet, but by our expansion across the cosmos. The technical capabilities NERVA represented would have opened doors that remain closed today. But we'd also have normalized atmospheric nuclear operations. Each launch would have added to the planet's radioactive burden. Accidents would have been inevitable. A launch failure scattering reactor material across populated areas, a malfunction during orbital insertion, a collision in space spreading nuclear debris. The cumulative cancer toll would have mounted silently, invisibly, a price paid by people who never consented and never benefited. We might have Mars, but we'd also have a more contaminated Earth. We might have reached the stars, but at the cost of poisoning our home. The story of NERVA isn't just about what we lost. It's about what we learned, and what we're still struggling with today. We learned that technical possibility doesn't equal moral imperative. We learned that the most important engineering challenge isn't building more powerful engines, but building wisdom to match our capabilities. We learned that sometimes the most courageous decision isn't to push forward, but to step back. Today, as we stand on the edge of a new space age with commercial spaceflight, renewed lunar ambitions, and Mars missions on the horizon, NERVA's ghost haunts us. NASA is researching nuclear thermal propulsion again, but with modern safety standards, different reactor designs, and decades of additional knowledge about radiation effects. The dream hasn't died, it's evolved. We still want Mars, but we want to get there without statistical death sentences and radioactive exhaust. The question isn't whether we'll use nuclear propulsion, but when and how we'll do it responsibly. The engineers who built NERVA weren't villains. They were visionaries who pushed boundaries, asked uncomfortable questions, and ultimately helped us understand where those boundaries should be. They gave us a gift, though perhaps not the one they intended. They showed us that we're capable of building almost anything we can imagine. But they also showed us that capability alone isn't enough. We need wisdom, restraint, and the courage to say no to our own ambitions when the cost is too high. In a bunker in Nevada, there's probably still equipment from those tests in 1968, too radioactive to move, slowly decaying over decades and centuries. It's a monument to what we almost became, a species willing to poison our own planet in pursuit of others. The fact that we chose differently, that we canceled NERVA despite its technical success, might be one of humanity's finest moments. Not because we gave up on Mars, but because we refused to get there by leaving bodies in our wake. We're still going to Mars. We're still going to the stars. But we're going to do it right, or not at all. That's the real legacy of NERVA. Not the rocket we built, but the rocket we chose not to fly. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching. On a frozen morning in Kazakhstan, Soviet engineers ignited a rocket engine that burned hotter than the surface of a star. The RD-0410 nuclear thermal rocket, a machine that used a live nuclear reactor as its beating heart, achieved what American scientists thought impossible, a specific impulse of 910 seconds, crushing the performance of NASA's best nuclear engine by a comfortable margin. For a brief moment, the Soviet Union had won the ultimate prize in the space race, the key to Mars and beyond. But this wasn't just a triumph of engineering. It was a gamble with consequences that could have dwarfed Chernobyl. To understand why this engine represented such a pivotal moment in the Cold War, you first need to understand what makes nuclear thermal rockets the holy grail of space propulsion. Imagine you're trying to reach Mars using conventional chemical rockets, the kind that powered the Apollo missions to the moon. You're essentially burning sophisticated kerosene or hydrogen with oxygen, creating hot gas that shoots out the back of your spacecraft. It works, but it's fundamentally limited by chemistry. The molecules can only get so hot, only move so fast, before the laws of thermodynamics say, that's it, that's all you get. Now imagine a different approach. Instead of burning fuel, you take liquid hydrogen, the lightest element in the universe, and you run it through the core of a nuclear reactor. Not near it, not around it, through it. The reactor heats that hydrogen to temperatures that would vaporize steel, turn tungsten into vapor, make diamonds sublimate into carbon gas. Then you expel that superheated hydrogen through a nozzle, and suddenly you're playing a completely different game. You've nearly doubled your efficiency. Where a chemical rocket might give you 450 seconds of specific impulse, a measure of how effectively you're converting propellant into thrust, a nuclear thermal rocket could theoretically deliver 900 seconds or more. This isn't just an incremental improvement. This is the difference between Mars being a distant dream and Mars being a destination you could reach within a human lifetime, literally. With chemical rockets, a round trip to Mars takes over 2 years, exposing astronauts to cosmic radiation, bone density loss, and psychological stress that pushes the limits of human endurance. With nuclear thermal propulsion, you could cut that time in half, maybe more. You could make Mars missions not just possible, but practical. The Americans understood this. In 1963, NASA and the Atomic Energy Commission launched the NERVA program, Nuclear Engine for Rocket Vehicle Application. Over the next decade, they would spend approximately $1.4 billion developing nuclear rocket technology. By 1969, American engineers had achieved specific impulse values between 825 and 850 seconds with their hot bleed cycle design, and were projecting 850 to 875 seconds with an improved expander cycle configuration. They built test reactors. They fired them at the Nevada test site. They proved the concept worked. But across the Iron Curtain, Soviet intelligence was watching, and what they saw both terrified and tantalized them. The space race had been defined by a series of Soviet firsts. First satellite, first human in space, first spacewalk, followed by the crushing American triumph of the moon landing. The Soviet lunar program had failed. Their N-1 rocket had exploded spectacularly, repeatedly. They needed something to restore their prestige, to prove that Soviet engineering could still lead humanity into the cosmos. Valentin Glushko, the influential chief designer at KB Energomash, saw nuclear thermal propulsion as that opportunity. Here was a technology still in its infancy, where American advantages in computing and miniaturization mattered less than raw engineering prowess and a willingness to take risks. If the Soviet Union could build a superior nuclear rocket engine, they could leapfrog American technological advantages and make Mars missions feasible within budget constraints that wouldn't bankrupt the state. The Americans had shown it was possible. The Soviets would show it could be perfected. But Glushko faced fierce resistance. Chemical rocket engineers, the establishment that had built the R-7, launched Sputnik, sent Gagarin into orbit, dismissed nuclear propulsion as too dangerous, too expensive, too far from practical deployment. Why chase this fever dream when proven chemical rockets could still accomplish so much? The debates within Soviet design bureaus grew heated. Nuclear propulsion was unproven. It was reckless. It was exactly the kind of technological moonshot that could destroy careers and waste resources that could be better spent on incremental improvements to existing systems. Then intelligence reports confirmed NERVA's progress. The Americans weren't just theorizing. They were building hardware, conducting tests, achieving results. political pressure mounted from the highest levels of Soviet leadership. The Soviet Union could not afford to fall behind in yet another space technology. Not after the moon. Not when the propaganda value of being first to Mars could reshape the global perception of socialist technological superiority. The project received official approval. The man chosen to lead the technical development was Nikolai Konyukov, a brilliant engineer at KBKHA Voronezh. Konyukov was a perfectionist, someone who understood that the difference between a functioning nuclear rocket and a radioactive catastrophe lay in the precision of every weld, every calculation, every material's choice. He was also acutely aware that he was being asked to solve problems that had stymied the best American engineers, and he was being given less money and less time to do it. The challenge was brutally simple in concept, nightmarishly complex in execution. A nuclear thermal rocket requires a reactor core that can operate at temperatures exceeding 3,000 Kelvin while being bombarded by its own neutron flux, cooled by cryogenic hydrogen flowing at high pressure, and controlled precisely enough that it doesn't melt down or explode. The fuel elements, the actual uranium-containing rods through which the hydrogen flows, must maintain their structural integrity under conditions that would destroy almost any known material. The American NERVA program had struggled with fuel element cracking. Their designs used a graphite matrix with uranium carbide particles, and while this worked for short test firings, the thermal stress and neutron bombardment caused microscopic cracks that propagated over time. If a fuel element failed catastrophically during operation, you could have a partial reactor meltdown combined with a hydrogen explosion. Not ideal for a spacecraft. Konyukov's team at KBKHA Voronezh, working with nuclear physicists from the Kurchatov Institute, developed an innovative solution. Instead of copying NERVA's approach, they would learn from its weaknesses. The RD-0410 design incorporated thermal insulation between the uranium carbide and tungsten carbide fuel elements and the zirconium hydride moderator. This allowed for a more compact reactor core while managing the extreme temperature gradients more effectively. But the real innovation was in the hydrogen flow pattern. Rather than flowing hydrogen directly through the hottest parts of the reactor first, the RD-0410 design cooled the moderator first. This maintained low neutron energy and high fission cross-section, keeping the nuclear reaction stable and controllable. Then the hydrogen made direct contact with the fuel rods, heating to extreme temperatures. To prevent chemical reactions between the hydrogen and the carbide fuel, reactions that could weaken the fuel elements, the engineers added hexane to the hydrogen. It was an elegant solution to a problem that had plagued earlier designs. The target specifications were ambitious but achievable. 35.2 kilonewtons of thrust, 910 seconds of specific impulse, and an operational lifetime of 1 hour, 3,600 seconds of continuous burn time. That might not sound like much, but for deep space maneuvers, an hour of thrust from a nuclear engine could accomplish what would take days or weeks with chemical propulsion. The theoretical work was brilliant, the engineering was sound, but theory and practice are separated by a chasm that can only be crossed through testing, and testing a nuclear rocket engine requires facilities that most nations cannot even contemplate building. The chosen location was the Semipalatinsk test site in Kazakhstan, a vast expanse of steppe that had already been contaminated by hundreds of nuclear weapons tests. If anywhere on Earth could be considered expendable for nuclear experimentation, this was it. The test stand was a massive concrete and steel structure, engineered to contain, theoretically, even a reactor meltdown. Radiation monitoring stations ringed the facility in concentric circles, their sensors calibrated to detect the slightest anomaly in neutron flux or gamma radiation. But as Konyukov's team prepared for actual testing, they confronted an uncomfortable truth. They were operating at the edge of human knowledge. Every calculation, every safety protocol, every emergency procedure was based on models and assumptions that had never been validated at this scale, under these conditions. They were about to pump cryogenic liquid hydrogen through a functioning nuclear reactor, creating temperatures and pressures that existed nowhere else on Earth outside of weapons tests and stellar interiors. The first tests weren't even nuclear. Before you dare to achieve criticality, you run cold flow tests, pumping hydrogen through the system without initiating the nuclear reaction, checking for leaks, validating your instrumentation, making sure the basic plumbing works. These should be routine. They should be safe. They were anything but. The reality of working with liquid hydrogen at these scales and pressures proved far more treacherous than the models predicted. Hydrogen is the smallest molecule. It finds leaks that would contain any other substance. It diffuses through materials that seem solid, and when it mixes with air and finds an ignition source, it explodes with terrifying efficiency. The engineers knew this intellectually, but knowing something in theory and experiencing it in practice are entirely different things. Despite the setbacks, despite the growing awareness that they were dancing on the edge of catastrophe, political pressure demanded results. The program had consumed enormous resources. The leadership wanted vindication, and in 1985, the RD-0410 would finally face its ultimate test, a full-power nuclear burn that would either validate years of work or confirm the skeptics' worst fears. Konyukov watched from the control bunker, separated from the test stand by thick concrete and several kilometers of contaminated steppe. His life's work was about to be validated or destroyed. Around him, technicians monitored instrument panels, their faces illuminated by the glow of readouts and oscilloscopes. Everyone understood what was at stake. This wasn't just a test. This was the moment that would determine whether the Soviet Union could claim technological superiority in the most demanding arena of space propulsion. The test sequence began with the careful ballet of achieving criticality. Control rods withdrew from the reactor core in precise increments, allowing the neutron flux to build gradually. Temperature sensors tracked the rising heat in the fuel elements. When the reactor reached operating temperature, liquid hydrogen began flowing through the cooling channels in the moderator, then through the fuel elements themselves. What happened next was, by any measure, a triumph of engineering. The RD-0410 achieved a specific impulse of 910 seconds, definitively surpassing the American NERVA program's best performance of 850 seconds. That 7% advantage might sound modest, but in the mathematics of rocket propulsion, it translates to dramatically reduced propellant requirements. For a Mars mission, that difference could mean the distinction between a mission that requires 2 launches to assemble in orbit and one that could depart from a single launch. It could mean the difference between a spacecraft that masses 800 tons and one that masses 600 tons. It could mean the difference between a mission that's theoretically possible and one that's actually affordable. The reactor temperatures exceeded 3,500 Kelvin, in some regions of the core, approaching 3,700 Kelvin. To put that in perspective, the surface of the Sun is about 5,800 Kelvin. The RD-0410 was creating conditions inside its reactor core that were more than half as hot as the surface of our star. This was hotter than the melting point of tungsten, one of the most heat-resistant materials known to science. The fact that the fuel elements maintained their integrity at these temperatures represented a genuine breakthrough in materials science and nuclear engineering. The engine ran for its planned duration, demonstrating stable operation and controllable thrust. The hydrogen exhaust, superheated to temperatures that turned it into a plasma, screamed from the nozzle at velocities that pushed the boundaries of what measuring instruments could track. Every sensor, every data point, confirmed what the engineers had calculated. The RD-0410 worked. It was real. The Soviet Union had built a nuclear rocket engine superior to anything the Americans had achieved. But in the immediate aftermath, as champagne bottles were being prepared and congratulatory telegrams drafted, Konyukov's team was examining the post-test data with growing unease. Radiation monitors had detected unexpected neutron flux patterns during the burn. The distribution wasn't quite what the models had predicted. Something in the reactor core wasn't behaving exactly as designed. When they could finally approach the test stand and begin inspecting the engine, the source of the anomaly became clear. Several fuel elements showed microscopic cracks, stress fractures caused by the extreme thermal cycling and neutron bombardment. The cracks were tiny, barely visible even under magnification, but their implications were enormous. If the test had run just 20% longer, those cracks could have propagated. A fuel element could have ruptured. And a ruptured fuel element in an operating nuclear thermal rocket is the beginning of a nightmare scenario. Loss of structural integrity leading to uneven cooling, leading to localized overheating, potentially triggering a cascade failure that could result in a partial reactor meltdown. The success had been real, but it had also been a near catastrophe averted by luck and conservative test planning. They had proven the concept worked, but they had also proven that their margins were far thinner than anyone wanted to admit. The environmental monitoring told an even more sobering story. Post-test analysis revealed significant radioactive contamination of the test site, far exceeding predictions. Isotopes that would remain hazardous for decades had been dispersed across the steppe. The models had underestimated how much radioactive material would be released during operation. Medical monitoring of test personnel showed elevated radiation exposure levels. Several technicians developed symptoms consistent with acute radiation syndrome, though thankfully not at life-threatening doses. These were the people who had believed the safety protocols would protect them, who had trusted the calculations that said the exposure levels would be acceptable. Yevgeny Velikov, the Kurchatov Institute physicist who had provided crucial nuclear expertise to the program, found himself compiling an internal report that became increasingly difficult to write. The data was unambiguous. The RD-0410 worked, but only barely, and only under controlled ground conditions. The fuel elements could survive a 1-hour burn, but showed signs of degradation that suggested they couldn't survive the multiple burns that an actual Mars mission would require. The radiation release was manageable at a remote test site, but what would happen if such an engine failed during launch, scattering radioactive material across a populated area? The fundamental problem was one of materials science. No known material could withstand the combination of extreme temperatures, intense neutron bombardment, and thermal cycling for the extended periods required for actual deep space missions. You could make it work once, maybe twice, under ideal conditions. But the reliability needed for human spaceflight, where failure means not just a lost mission, but dead cosmonauts, remained out of reach. Velikov's report documented these concerns with scientific precision. He recommended against flight testing without major design revisions. Revisions that would essentially require starting over, developing entirely new materials, rethinking the fundamental architecture of the engine. The report was classified immediately. The environmental monitoring data was never shared with local populations living downwind of Semipalatinsk. The medical data on exposed workers was buried in archives that wouldn't be opened for decades. Meanwhile, 8,000 kilometers away, American engineers who had worked on NERVA were reaching eerily similar conclusions. The parallel is striking, almost uncanny. Two superpowers, ideologically opposed, competing fiercely for technological supremacy, independently developing similar technologies, and independently discovering the same fundamental limitations. The American NERVA program had conducted multiple test firings at the Nevada test site between 1964 and 1969, achieving specific impulse values between 825 and 850 seconds with their hot bleed cycle design. Like their Soviet counterparts, they had encountered fuel element cracking, materials degradation, and concerning radiation release. Unlike their Soviet counterparts, American engineers had to contend with a growing environmental movement that made nuclear testing increasingly politically toxic. Nevada test site contamination became a public controversy. Activists demanded transparency. Scientists who had worked on nuclear weapons programs were beginning to speak out about the long-term health effects of radiation exposure. In 1972, the NERVA program was officially canceled. The public explanation cited budget cuts and shifting priorities. NASA was moving away from ambitious deep space missions and focusing on the Space Shuttle program. But internal NASA documents revealed that safety concerns were a major factor in the decision. The engineering margins were too thin, the consequences of failure were too severe, and the political will to continue testing nuclear rockets in Earth's atmosphere was evaporating. The Soviet program continued for more than a decade after NERVA's cancellation, but it was following a parallel trajectory toward the same conclusion. The laws of physics and materials science don't care about political systems. Both sides hit the same technological wall. Both sides discovered that while nuclear thermal rockets could work in principle, the gap between principle and practice was filled with radioactive hazards, materials science challenges, and safety concerns that couldn't be wished away through ideological conviction or national pride. The RD-0410 represented the pinnacle of Soviet nuclear rocket development. It achieved specifications that exceeded American capabilities. It demonstrated that Soviet engineering could match and surpass Western technology in one of the most demanding fields of aerospace development. But it also demonstrated the limits of what Cold War-era technology could safely accomplish. The Kurchatov-Mars 1994 mission concept, a nuclear thermal rocket-powered spacecraft that would carry cosmonauts to Mars and back, remained on the drawing boards. The engine existed, the test data existed, the political will existed, but the fundamental problems remained unsolved. How do you make fuel elements that can survive multiple burn cycles? How do you ensure that a launch failure doesn't scatter radioactive debris across a wide area? How do you convince the international community that launching nuclear reactors into space is acceptable? These questions didn't have good answers in 1985, and the collapse of the Soviet Union in 1991 ensured they wouldn't be answered by the program that had come so close to making nuclear space propulsion a reality. The RD-0410 program was quietly terminated. The test data was classified. The engines that had been built were placed in secure storage. The engineers moved on to other projects or retired, carrying with them the knowledge of what they had achieved and what they had narrowly avoided. Today, the RD-0410 exists in a strange liminal space in the history of space exploration. It was a genuine technological achievement, a machine that worked, that exceeded its design specifications, that demonstrated capabilities that remain impressive even by modern standards. But it was also a cautionary tale about the dangers of pushing technology faster than our ability to control it safely, about the environmental and human costs of Cold War competition, about the gap between what we can build and what we should build. The dream of nuclear thermal propulsion hasn't died. Modern programs are revisiting the concept, armed with better materials science, more sophisticated modeling, and a deeper understanding of the challenges. But they're building on the lessons learned by the engineers who built NERVA and the RD-0410, lessons purchased at the cost of contaminated test sites and exposed workers, lessons written in classified reports and declassified decades later. The Soviet nuclear rocket that beat America was real. It worked. It represented a genuine triumph of engineering and scientific ambition. But it also revealed a truth that transcends Cold War politics. Some technologies are so powerful, so dangerous, that building them successfully is only the first challenge. The harder challenge is building them safely enough that we can actually use them. And in 1985, on a frozen morning in Kazakhstan, Soviet engineers discovered that they had won the race to build the better nuclear rocket, but they hadn't yet solved the problem of how to fly it without gambling with consequences that could dwarf any triumph. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching. Picture this: fuel elements glowing at 3,000 degrees Celsius, hotter than the temperature at which diamond vaporizes, contained within a graphite structure mere centimeters from liquid hydrogen at -253 degrees Celsius. A temperature differential so extreme that most materials would explode on contact. This wasn't a thought experiment. This was NERVA, the nuclear engine for rocket vehicle application. And in the Nevada desert, at a place called Jackass Flats, American engineers actually built it, tested it, and made it work. Imagine standing in your kitchen. Your oven, at its hottest, reaches maybe 260 degrees Celsius. Now multiply that by 12. That's the inferno NERVA engineers had to contain, and they had to do it while pumping liquid hydrogen, so cold it would freeze nitrogen solid, through channels carved into that same burning structure. The margin for error? Millimeters. The consequences of failure? Catastrophic. The NERVA reactor core contained hundreds of fuel elements arranged like a deadly honeycomb, each one a potential point of catastrophic failure. Engineers called them pencils, but these pencils were filled with uranium and had to survive temperatures that would turn steel into vapor, tungsten into puddles, and diamond into gas. Each fuel element was a cylindrical rod about 1 meter long and between 1 and 2 centimeters in diameter, roughly the size of a thick broomstick. Hold a broomstick in your hands right now, feel its weight, its simplicity. Now imagine that simple cylinder containing the power to destroy itself 1,000 times over, every single second, while somehow remaining intact, long enough to push a spacecraft to Mars. Inside that deceptively simple geometry lurked extraordinary complexity. Cooling channels drilled through a matrix of uranium dioxide suspended in graphite, arranged in a hexagonal pattern designed to maximize every square millimeter of heat transfer surface area. These weren't just reactor components. They were the entire foundation upon which humanity's dreams of reaching Mars would stand or fall. The operating conditions these elements faced defied comprehension. At full power, fuel element temperatures soared to 3,000 degrees Celsius. Meanwhile, liquid hydrogen at negative 253 degrees Celsius screamed through those cooling channels at tremendous velocity. A temperature differential of over 3,000 degrees across the span of a few centimeters. To put that in perspective, if you could somehow touch both surfaces simultaneously, one hand would freeze solid in milliseconds, while the other would vaporize before your nerves could even register pain. Most known materials would shatter instantly under such thermal violence. The graphite-uranium matrix had to absorb this punishment while maintaining structural integrity, because a single failed element could trigger a cascade that would destroy the entire reactor core. Harold Finger, the NASA and Atomic Energy Commission program manager orchestrating this Herculean effort, stood before rooms of skeptical politicians and military officials, selling them on an engine that defied conventional wisdom. His pitch was audacious. A nuclear rocket could cut Mars mission time in half, with twice the efficiency of chemical rockets, the holy grail of deep space exploration. But behind those confident presentations, Finger knew his team at Westinghouse and Aerojet was about to confront engineering problems that had no textbook solutions. The weight of America's space ambitions rested on his ability to deliver the impossible. The early test results were catastrophic. Thermal shock caused massive cracking during rapid temperature changes as the reactor ramped to full power. The fuel elements would literally tear themselves apart as their outer surfaces expanded while their cores remained cold. Imagine a glass cup plunged into boiling water. Now multiply that stress by 1,000. But that was only the beginning of the nightmare. Inside the reactor, intense radiation bombardment created gas bubbles in the fuel matrix and displaced atoms from their crystalline positions, slowly destroying the material's structural integrity from within. It was like watching a building's foundation turn to sand, one grain at a time, while people still lived inside. And perhaps most insidiously, the hydrogen itself, the very substance they needed for propulsion, became a corrosive agent at these extreme temperatures, attacking the graphite matrix, forming methane, and causing steady mass loss that would eventually compromise the entire element. The hydrogen they needed to cool the reactor was simultaneously dissolving it from the inside out. Westinghouse engineers found themselves fighting a war on 3 fronts simultaneously, armed with machining and coating techniques never before attempted. They had to fabricate hundreds of these elements with microscopic precision, knowing that imperfections invisible to the naked eye could prove fatal at operating temperatures. A scratch, 1/10 the width of a human hair, could become a crack. A crack could become a rupture. A rupture could become a meltdown. The breakthrough came during a late-night brainstorming session when someone proposed zirconium carbide cladding, a protective coating that could withstand both the infernal heat and the hydrogen's chemical assault. It was a gamble born of desperation. The material itself was barely understood. Its behavior at these extreme conditions was theoretical at best. The next high-power test run would either validate years of work or send the team back to the drawing board, back to square one, with the space race clock ticking relentlessly forward. The zirconium carbide survived. More than survived, it excelled. When the improved Phoebus reactor roared to life and sustained full power for 90 minutes, post-test inspections revealed less than 1% mass loss in the coated fuel elements. The honeycomb of hell had been tamed, at least enough to prove the concept could work. But surviving extreme heat was only the first challenge. The reactor had to be controlled with surgical precision, throttled in real time, and, most audaciously, restarted in the vacuum of deep space. This required an innovation that seemed impossibly simple: rotating drums. How do you dim a nuclear reactor like a light switch? This wasn't a theoretical question. It was an engineering requirement. Mars missions would require precisely calibrated engine burns, and the crew's lives would depend on mission success. Every restart in the vacuum of space, every throttle adjustment during orbital maneuvers. The control system couldn't just work, it had to be foolproof. The solution seemed almost absurdly simple: rotating drums. Surrounding the reactor core, 12 cylindrical control drums stood like sentinels. Each drum had two faces, one side coated with neutron-absorbing material, either boron or hafnium, the other side lined with neutron-reflecting graphite. Rotating the drums modulated the reactor's neutron flux and power output. A neutron-absorbing surface captures neutrons, reducing the fission reaction. A reflecting surface bounces neutrons back into the core, amplifying the chain reaction. It was elegant, it was mechanical, and it had to work flawlessly at temperatures that would destroy conventional actuators. Think of it like this. Imagine trying to control the sun's brightness by positioning mirrors around it. Now imagine those mirrors have to work while bathed in temperatures that melt titanium and radiation intense enough to kill you in seconds, and they have to respond to commands in fractions of a second with positioning accuracy measured in tiny fractions of a degree. That was the challenge. The precision was staggering. The control drum system could throttle the reactor in increments as small as 1% of full power. During steady-state operation, test logs showed power fluctuations of less than 2%, a high level of precision. But NERVA needed speed. The system could transition from full power to complete shutdown in under 30 seconds. 30 seconds between a roaring nuclear inferno and cold silence. This capability countered one of the most persistent myths about nuclear rockets, that once started, they couldn't be shut down or restarted. Internal NASA memos reveal the truth. Engineers at Jackass Flats demonstrated restart capability repeatedly during ground tests. Some engines were shut down, left to cool for hours, then restarted and brought back to full thrust. The reactor wasn't a one-shot device. It was a throttleable engine, controllable with the finesse required for complex interplanetary maneuvers. But those same internal documents exposed the engineers' deepest anxieties. Would the actuators survive? The drums had to rotate smoothly in an environment bathed in intense radiation and searing heat, conditions that could seize mechanical components or degrade electronics into useless slag. Memos circulated through Marshall Space Flight Center, describing worst-case scenarios. A drum stuck in the wrong position, unable to shut down the reactor, or unable to restart it when needed millions of kilometers from Earth. Imagine being halfway to Mars when your engine refuses to start. No AAA tow truck is coming. no rescue mission is possible. You would simply drift through space until your life support failed. The response was characteristically methodical. Redundant control mechanisms were designed into every drum. Rigorous cycle testing pushed the actuators through thousands of rotations, simulating years of operation compressed into weeks of torture testing. Engineers designed mechanical backups that could force the drums into shutdown position, even if primary systems failed. A final failsafe when all else went wrong. Harold Finger understood what was at stake. He described the control drum system as the key to making nuclear propulsion practical. Without precise, reliable throttling, he noted in program reviews, the engine would be nothing more than a one-shot device, useless for the complex ballet of burns, coasts, and course corrections that Mars missions demanded. The drums weren't just a control system. They were the difference between a laboratory curiosity and a machine that could actually take humans to another planet. With fuel elements that could survive diamond vaporizing heat and a control system that could modulate power with surgical precision, NERVA had conquered the reactor itself. But there remained one final, seemingly insurmountable challenge. How do you channel 3,000-degree hydrogen through a nozzle without melting it into slag? The exhaust from a NERVA engine was hot enough to vaporize most conventional nozzle materials without advanced cooling techniques. Worse, the reactor was broadcasting lethal radiation in all directions. Solving these problems required engineering solutions that seemed to defy physics itself. The nozzle had to channel hydrogen exhaust at over 2,000 degrees Celsius, while surviving chamber pressures between 400 and 800 pounds per square inch. Imagine standing at the bottom of the ocean with the weight of 800 feet of water pressing down on you. Then multiply that pressure by 10 and add heat that would vaporize rock. That's what the nozzle experienced, continuously, for hours. The solution was regenerative cooling, a concept borrowed from high-performance rocket engines, but pushed to its absolute limits. Engineers circulated liquid hydrogen through intricate channels machined into the nozzle walls before that same hydrogen entered the reactor core. It was like an ice skater gliding on a thin layer of water. The margin between success and catastrophic failure was razor thin. The supercooled hydrogen absorbed heat from the nozzle surface, creating a protective barrier that kept the metal just below its melting point. But early tests revealed that theory and reality rarely agreed. Technical reports from Jackass Flats document how the first nozzle designs suffered erosion and cracking during long-duration firings. The thermal gradients were simply too extreme. The Westinghouse and Aerojet teams, engineers working in shielded bunkers, their safety dependent on readings displayed on screens showing radiation levels in real time, went back to the drawing board. They relied on remote cameras and banks of Geiger counters, watching the tests from a safe distance, their fate tied to the readings on those screens. One engineer later recalled, "We were essentially building a controlled nuclear explosion and trusting that it would point the right way." Those who witnessed full-power engine firings described it as unforgettable. The ground shook, the air shimmered with heat distortion, and the exhaust roared like a miniature sun. It was a visceral reminder of the forces they were attempting to harness and control. Each test was a gamble. Each successful run was a small miracle. The teams developed composite linings made from niobium and graphite with cooling channels so intricate they required new machining techniques to fabricate. Each iteration brought them closer, each test firing providing data no computer model could predict. This was engineering at the edge of the possible, where every assumption had to be tested, every calculation verified in fire and radiation. Then there was the radiation problem, arguably more insidious because it was invisible. The reactor produced intense neutron and gamma radiation that could kill astronauts in minutes if left unshielded. Engineers designed multi-layered shields of lithium hydride, boron carbide, and tungsten, the invisible armor, materials chosen for their ability to absorb different types of radiation. Think of it as building walls that could stop bullets you couldn't see, traveling at nearly the speed of light. Test stand measurements at Jackass Flats confirmed the shield's effectiveness, reducing crew exposure below 0.05 sieverts for typical mission profiles, meeting NASA's safety standards. But the mass penalty was brutal. These shields weighed between 2,000 and 6,000 kilograms, roughly the weight of 2 to 6 cars. They represented 5 to 10% of the total engine mass. Every kilogram of shielding was a kilogram not available for payload, scientific instruments, or supplies. The trade-off sparked heated internal debates. How much radiation exposure was acceptable? How much mission capability would you sacrifice to reduce crew risk by another fraction of a percent? There were no easy answers, only engineering compromises that felt inadequate no matter which way you calculated them. By 1972, the final performance metrics validated everything NERVA had promised. Thrust output reached 250,000 pounds-force in tests, enough to lift a fully loaded 747 aircraft straight up. Specific impulse measured between 850 and 900 seconds, exactly twice that of the best chemical rockets. To understand what that means, for every kilogram of fuel, NERVA could produce twice the push, twice the speed, twice the capability. It was the difference between reaching Mars in 8 months instead of 16, between survival and running out of supplies, between a mission that was possible and one that was merely theoretical. Engines ran at full power for over 60 minutes, with cumulative test time exceeding 17 hours across the entire program. The reactor could be throttled, shut down, and restarted reliably. The technology worked. All the impossible problems had been solved. The laws of thermodynamics had been tamed. Radiation had been contained. Materials that should have failed had been coaxed into survival. The engineers had won. But as engineers at Jackass Flats celebrated their final successful test, political winds in Washington were already shifting, and the program's fate was sealed not by engineering failure, but by budget cuts and changing priorities. The Apollo moon landings had been achieved. Public enthusiasm for Mars missions evaporated as Vietnam drained budgets and national attention. In 1973, the cancellation order came down. Harold Finger and the engineering teams, after years of solving impossible problems, conquering extreme temperatures, radiation, hydrogen embrittlement, and precision control, received the news that the program was terminated not because it failed, but because America's priorities had shifted. The personal devastation was profound. Engineers who had sacrificed years to make the impossible real, who had worked in radiation-soaked test bunkers, who had solved problems that had no textbook answers, watched as their life's work was dismantled. The test stands at Jackass Flats were shut down. Teams were disbanded. Decades of accumulated knowledge scattered to the winds. NERVA's final scorecard was paradoxically perfect and pointless. Over 20 successful reactor tests, proven technology, cleared for flight, but no mission to fly. The infrastructure was dismantled, the expertise dispersed, the dream deferred. The cruel irony haunted everyone involved. They had succeeded. They had built a controlled nuclear explosion and trusted that it would point the right way. And it did. But success wasn't enough. NERVA transformed from an impossible dream, containing a miniature nuclear sun hot enough to vaporize diamond, into proven reality through the brilliance and determination of engineers who refused to accept that the laws of physics were insurmountable. They conquered temperature differentials that should have destroyed any material. They tamed deadly radiation that could kill in seconds. They solved hydrogen embrittlement that dissolved their reactor from the inside out. They built precision control systems that worked flawlessly in conditions that would destroy conventional machinery. The transformation wasn't just technical, it was a testament to human ingenuity's ability to overcome seemingly impossible challenges. But it also revealed a harder truth, that the greatest barriers to space exploration aren't always the laws of thermodynamics. Sometimes they're the limits of political vision and sustained commitment. Somewhere in the Nevada desert, the test stands at Jackass Flats still stand silent, monuments to the day we built an engine that could take us to Mars, and then chose not to go. The engineers who wrestled with the impossible and won proved that we could contain a nuclear sun, dance on the razor's edge between fire and ice, and point a controlled explosion exactly where we wanted it. NERVA didn't fail. We just stopped believing the destination was worth the journey. Today, as NASA plans new Mars missions and private companies dream of interplanetary travel, NERVA's innovations in materials science, high-temperature engineering, and radiation shielding continue to influence reactor design. The technology sleeps, but it doesn't die. The question that haunts us isn't whether we can build a nuclear rocket. NERVA proved we can. The question is whether we'll find the will to finish what those engineers started. Which of NERVA's engineering challenges seems the most impossible to overcome? The 3,000-degree temperatures, mere centimeters, from supercooled hydrogen. The hydrogen that simultaneously cooled and corroded the reactor, the radiation shielding that had to stop invisible death, or the precision control systems that had to work flawlessly millions of kilometers from help. And if you think nuclear propulsion deserves another chance for Mars missions, tell me why or why not. What would it take for humanity to pick up where these brilliant engineers left off? If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching. In the Nevada desert in 1963, American engineers embarked on something extraordinary, a program to build nuclear rocket engines that could revolutionize space travel. The NERVA program, Nuclear Engine for Rocket Vehicle Application, successfully proved that atomic power could propel spacecraft with efficiency that chemical rockets could only dream of. They achieved specific impulse of 811 seconds, nearly double that of the best chemical engines, with later designs targeting 825 seconds. Then, in 1973, after spending nearly $2 billion, they shut it down and buried the test engines at the Nevada test site, literally interring America's nuclear propulsion dreams in the desert sand. For 50 years, those engines remained buried, both physically and in the national consciousness. Nuclear thermal rockets became a taboo subject, associated with Cold War paranoia and environmental fears that no politician dared resurrect. But in 2021, everything changed. China announced its own nuclear thermal rocket program, with Dr. Zhang Yulin providing a timeline for crewed Mars missions using this technology by the 2040s. Suddenly, America's abandoned technology became a critical national security vulnerability. Now, the United States is scrambling to resurrect what it buried decades ago through DRACO, the Defense Advanced Research Projects Agency's ambitious gamble to reclaim American dominance in space before it's too late. The question isn't whether nuclear rockets will revolutionize space travel. The question is, which flag will they carry? To understand why America is frantically reviving this technology, we need to confront the ghost that still haunts it, the spectacular rise and mysterious fall of NERVA. The program was formally established in 1963, evolving from the earlier Project Rover after NASA took a leading role in developing nuclear thermal propulsion for space applications. It was the golden age of American space ambition, when anything seemed possible, and the race to the moon demanded technologies that pushed every boundary. The engineers working on NERVA weren't just building rocket engines, they were crafting the keys to the solar system, and it worked. The NERVA A2 test achieved that remarkable 811 seconds of specific impulse, proving the fundamental concept was sound. To put that in perspective, imagine you're driving two cars across the country. One gets 25 miles per gallon. That's your chemical rocket. The other gets 50 miles per gallon. That's NERVA. You'd reach your destination using half the fuel, or you could go twice as far on the same tank. In space, where every kilogram of propellant costs thousands of dollars to launch, that difference isn't just significant, it's revolutionary. But three fatal flaws conspired to kill the program. First, costs were escalating dramatically. The Vietnam War was devouring the federal budget, and NASA's priorities were shifting away from ambitious deep space missions. By the time NERVA was terminated in 1973, it had consumed nearly $2 billion, an astronomical sum that became impossible to justify. Second, there was no committed mission that actually required nuclear thermal propulsion. The Apollo program was winding down, and the grand visions of Mars expeditions that might have justified NERVA's expense evaporated in the political realities of the early 1970s. Third, public and political concerns about nuclear safety and environmental risks grew louder, especially with no clear near-term application to show for the investment. When the program ended, those test engines were buried at what is now the Nevada National Security Site. It was both a practical disposal measure and a symbolic burial of America's atomic space dreams. For half a century, they lay there, forgotten monuments to abandoned ambition, until China forced America to remember. The announcement of China's nuclear thermal rocket program in 2021 sent shockwaves through the American space establishment. Here was a geopolitical rival openly pursuing the same technology that the United States had perfected and then abandoned. Dr. Zhang Yulin's timeline, pointing to the 2040s for crewed Mars missions, suddenly made America's buried engines look less like wise restraint and more like strategic negligence. The question became urgent. If NERVA was so promising, why did it take a rival superpower to force America's hand? The answer lies in what makes nuclear rockets so powerful, and why that power is worth resurrecting, despite the ghosts of the past. The fundamental physics of nuclear thermal propulsion are elegantly simple, even if the engineering is brutally complex. Instead of burning chemical fuel, which is really just rearranging molecular bonds to release energy, a nuclear reactor uses atomic fission to generate heat directly. That heat is transferred to hydrogen propellant, raising it to extreme temperatures exceeding 2,500 degrees Celsius. The superheated hydrogen then expands through a nozzle and rockets out at tremendous velocity, producing thrust. No combustion required, just pure thermal expansion driven by nuclear fire. This is where specific impulse becomes critical. Think of specific impulse as the miles per gallon rating for rocket engines. It measures how efficiently an engine converts propellant into thrust. Chemical rockets, limited by the energy available in molecular bonds, top out around 450 seconds. The Draco program is targeting around 900 seconds, essentially doubling the efficiency of the best chemical systems. It's not an incremental improvement, it's a revolution. What does that mean in practical terms? Consider a Mars mission. With chemical propulsion, the journey takes 6 to 9 months of continuous exposure to cosmic radiation, zero-gravity muscle atrophy, and psychological stress. Every extra day in transit increases the risk to the crew and the complexity of life support systems. Nuclear thermal rockets could potentially cut that transit time to as little as 3 to 4 months, about half the duration. That's not just faster, it's fundamentally safer. Radiation exposure is reduced. Psychological strain is lessened. The mission becomes more survivable. But the strategic implications extend far beyond Mars. Whoever controls nuclear propulsion controls the ability to move rapidly anywhere in cislunar space. The vast region between Earth and the Moon that's becoming the new strategic high ground. They can respond to threats, inspect satellites, and establish presence at economically valuable locations like Lagrange points. They can reach asteroid resources that could be worth trillions of dollars. In short, nuclear thermal propulsion isn't just about exploration. It's about power projection in the ultimate high ground, space itself. Yet for all its promise, nuclear propulsion presents a central engineering paradox. To achieve these performance gains, Draco's reactor must operate at temperatures that would melt most known materials, while maintaining absolute containment of radioactive material. This is the challenge that defeated NERVA engineers working with 1960s technology. The reactor core is, quite literally, a miniature sun that must be controlled with absolute precision. One failure could scatter radioactive material across orbit, or, worse, back to Earth. The heart of the problem is the reactor core itself. NERVA used solid uranium fuel elements coated in graphite. At the extreme temperatures required for peak performance, these fuel elements degraded rapidly. The graphite would erode, the uranium would crack, and radioactive particles would contaminate the exhaust. Engine lifetime was limited, and each test left behind a trail of radioactive debris. For a technology that needed to operate for hours during an interplanetary mission, this was unacceptable. Modern materials science is providing answers that the NERVA generation could never access. The advanced nuclear fuel being developed for the Draco reactor is high-assay low-enriched uranium, or HALEU. This fuel can withstand far higher temperatures than NERVA's graphite uranium elements while maintaining structural integrity. It's a critical breakthrough that addresses one of the fundamental limitations that plagued the original program. But advanced fuel is only part of the solution. There's another insidious problem: hydrogen embrittlement. Liquid hydrogen, the propellant of choice because of its low molecular weight and high exhaust velocity, is extraordinarily reactive. At the molecular level, hydrogen atoms are so small they can actually penetrate the crystalline structure of metals. Once inside, they disrupt the atomic bonds that give metals their strength, causing catastrophic brittleness. A component that looks perfectly sound can suddenly shatter under stress because hydrogen has invisibly compromised its structure from within. This is where modern computational tools provide an advantage that NERVA engineers could only dream of. Computational fluid dynamics, CFD, allows supercomputers to simulate millions of scenarios, optimizing reactor geometry and predicting failure modes before building physical prototypes. Instead of expensive and time-consuming test and iterate cycles with actual hardware, engineers can now explore the entire design space virtually. They can model how hydrogen flows through the reactor core, where hotspots might develop, which materials will survive longest, and how to maximize performance while minimizing risk. It's the difference between exploring a dark cave with a flashlight and having a complete three-dimensional map before you enter. The progress has been remarkable. In recent high-fidelity ground tests, the Draco reactor containment system successfully demonstrated containment integrity under simulated operational conditions, a critical milestone that addresses one of the central safety concerns that doomed NERVA Zero measurable leakage: perfect containment. But here's the uncomfortable truth. These tests were conducted in controlled ground facilities, not in the violent environment of launch, where a rocket experiences crushing acceleration, or in the thermal extremes and radiation environment of space. The real test is still to come. Even the most brilliant reactor design is useless if the public won't accept it. This is where NERVA's ghost still haunts the program most powerfully. The very word nuclear carries baggage, decades of association with weapons, accidents, and environmental contamination. For Draco to succeed, it must overcome not just technical challenges, but deep-seated public fears and political resistance. This is perhaps the most difficult engineering problem of all: engineering public trust. The radiological risks fall into three scenarios. First, launch failure. The rocket explodes or crashes before the reactor is activated. Second, operational accident. The reactor malfunctions while operating in space. Third, re-entry. A spent reactor returns to Earth's atmosphere. Each scenario carries different risks and requires different mitigation strategies. Draco's safety approach addresses the launch failure scenario directly. The reactor remains cold, non-critical, until the spacecraft reaches high orbit, well above the atmosphere. This means that if a launch fails, what crashes back to Earth is non-radioactive uranium fuel, not highly radioactive fission products. It's still hazardous material, but it's not the catastrophic dispersal of intensely radioactive debris that nightmares are made of. The reactor only becomes hot once it's safely in space, where a malfunction wouldn't threaten Earth's surface. For spent reactors, the solution is the orbital graveyard concept, boosting them into stable disposal orbits that won't decay for thousands of years, far longer than the radioactive half-life of the materials involved. By the time these orbits naturally decay, the radioactivity will have diminished to background levels. It's not a perfect solution, but it's a manageable one that balances risk against strategic necessity. There's an economic argument that makes Draco more viable than NERVA ever was. While NERVA consumed nearly $2 billion in the 1970s, the projected total cost for the Draco demonstrator is significantly lower, thanks to advances in materials, computational modeling, and manufacturing. Modern tools allow engineers to accomplish in months what took NERVA teams years, and at a fraction of the cost. The program is expensive, certainly, but it's no longer the budget-devouring monster that NERVA became. Yet there's an uncomfortable geopolitical dimension to the safety debate. China's authoritarian system allows them to pursue high-risk, high-reward technologies without public debate, environmental review, or democratic accountability. They don't need to convince skeptical voters or navigate complex regulatory frameworks. They can simply decide and execute. This potentially gives them a decisive speed advantage in development, even if American technology is ultimately superior. It's a stark reminder that in the race for transformative technologies, democratic transparency can be both a strength and a vulnerability. The clock is ticking, and the timeline is unforgiving. China is constructing nuclear thermal rocket testing facilities in Inner Mongolia, visible evidence of their commitment to this technology. Dr. Zhang Yulin's timeline pointing to the 2040s for crewed Mars missions puts immense pressure on the United States to regain the initiative Draco's planned schedule calls for ground tests by 2026 and an in-space demonstration by 2027. It's an aggressive timeline that leaves little room for error or delay. What's at stake extends far beyond national pride. If China achieves operational nuclear propulsion first, they could establish facts on the ground, or rather, in space, before the United States can respond. They could claim strategic positions at Lagrange points, establish dominance in cislunar space, and potentially reach Mars first. The nation that controls nuclear propulsion will write the rules for humanity's expansion beyond Earth. They'll determine who has access to asteroid resources worth trillions of dollars. They'll control the strategic high ground that makes low Earth orbit look like a shallow puddle by comparison. This raises a profound question about democratic societies and technological competition. Can open societies, with their debates and accountability and safety reviews, compete with authoritarian regimes that face no such constraints when developing transformative technologies? The race to develop nuclear thermal rockets is becoming a test case for that question. It's not just about engineering anymore. It's about whether transparency and caution are luxuries we can afford when rivals are sprinting ahead, unburdened by public scrutiny. We began with a question. Why is America resurrecting a technology it buried 50 years ago? The answer reveals a profound transformation in how we understand space power. Nuclear thermal propulsion isn't just about faster trips to Mars. It's about who controls the strategic high ground of cislunar space, who can access the vast mineral wealth of asteroids, and ultimately, who writes the rules for humanity's expansion beyond Earth. The engineers of Draco aren't just building a rocket engine. They're fighting to ensure that the values of open societies, international cooperation, and transparent science shape humanity's future in space, rather than allowing authoritarian control of the solar system's most transformative technology. The ghost of NERVA has been exorcised not through forgetting the past, but by learning from its mistakes. Modern materials replace fragile graphite. Computational models replace guesswork. Rigorous safety protocols replace Cold War hubris. The NERVA engines buried in the Nevada desert were monuments to abandoned ambition. But perhaps they were never really abandoned, just waiting. Waiting for the materials science to catch up. Waiting for the computational tools to mature. Waiting for the geopolitical necessity to become undeniable. Those buried engines weren't failures. They were seeds planted in the desert, waiting for the right season to bloom. In the end, the race to develop nuclear thermal rockets isn't about America versus China, or democracy versus authoritarianism. It's about whether our species will remain trapped in Earth's gravity well, taking months to crawl between worlds, or whether we'll finally grasp the key to the solar system, the power of the atom, harnessed not for destruction, but for the greatest journey in human history. The engine that wins this race won't just take us to Mars faster. It will determine who we become among the stars. Which engineering challenge do you think is the hardest to overcome? The physics of containing a nuclear reactor in space, the political challenge of gaining public acceptance, or the geopolitical race against rival nations? Let us know in the comments. And if you want to see how other Cold War space technologies are being resurrected for the new space age, check out our video on nuclear pulse propulsion, the insane concept that makes Draco look tame by comparison. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching. In 1960, in a secure facility somewhere in America, engineers achieved something extraordinary. They built a nuclear reactor small enough to fit in a compact car that could power a spacecraft for years in the depths of space. The SNAP-2 reactor reached full operational capacity, 5 kilowatts of electrical power, enough to run sophisticated instruments far beyond the reach of the sun's light. It passed every ground test. It worked. But here's the thing nobody talks about. SNAP-2 never flew. Not because it failed, but because it succeeded, and in doing so, became trapped by the very forces that created it. This is the story of the nuclear reactor that could have changed everything, and the engineers who watched their masterpiece vanish into the shadows of history. To understand why SNAP-2 mattered, you need to understand the power problem that haunted every space engineer in the late 1950s. Picture yourself trying to design a mission to Jupiter. You've solved the rocket equation, you've figured out the trajectory. But then comes the question that kills dreams. How do you power your spacecraft for the 5-year journey? Solar panels? They're pathetically inadequate once you venture beyond the inner solar system, where sunlight dims exponentially with every mile traveled. Chemical batteries? They offer even worse prospects, degrading within months and adding crushing weight for minimal output. The mathematics were brutal and unforgiving. This was the impossible problem that landed on Harold Finger's desk. As director of the SNAP program, Systems for Nuclear Auxiliary Power, at the Atomic Energy Commission, Finger carried the weight of America's deep space ambitions on his shoulders. He understood what most people couldn't grasp. Without a revolutionary power source, humanity's reach would forever stop at Mars. Everything beyond, the gas giants, the outer solar system, the vast darkness between worlds, would remain eternally out of reach, not because we couldn't get there, but because we couldn't power anything once we arrived. Finger sat in planning meetings at NASA headquarters in 1959, making his case to skeptical administrators. His vision was audacious, a family of nuclear reactors specifically designed for space, with SNAP-2 targeting 3 to 5 kilowatts for satellite and deep space applications. The multi-kilowatt power sources would operate for years, maybe decades, in the harshest environment imaginable. But every time he presented his plans, he faced the same visceral pushback. You want to launch a nuclear reactor on a rocket? What if it explodes during launch? The specter of a radioactive disaster, debris raining down on populated areas, haunted every conversation. One accident, just one, could doom nuclear space power forever and turn public opinion into an insurmountable wall. Yet Finger had something more powerful than optimism. He had necessity on his side, and he had the Cold War. Rumors filtered through intelligence channels that the Soviet Union was developing their own space nuclear program. The space race, already fierce, now extended into power systems. Whoever solved the deep space power problem first would own the future of space exploration. The stakes couldn't be higher, and Finger knew it. America needed SNAP-2 to work, not just for scientific prestige, but for strategic dominance in the new frontier. But having a vision and building the machine are separated by an ocean of engineering nightmares. That's where the real story begins. In the hands of the engineers who had to transform Finger's dream into spinning atoms and flowing electrons. The SNAP-2 reactor that emerged from Atomics International was unlike anything built before. Previous nuclear reactors were massive installations, housed in concrete bunkers with cooling towers reaching toward the sky. SNAP-2 had to be different, compact enough to launch, light enough to reach orbit, and robust enough to operate in the vacuum of space without any of the safety systems terrestrial reactors took for granted. The engineering team faced constraints that would have seemed impossible just a decade earlier. At the heart of SNAP-2 sat a heterogeneous core design that represented a masterpiece of nuclear engineering. The fuel elements combined uranium with zirconium hydride, creating a material that served double duty. The uranium provided the nuclear fuel, while the zirconium hydride acted as a moderator, slowing down neutrons to sustain the chain reaction. Surrounding this core, beryllium and graphite reflectors bounced escaping neutrons back into the fuel, squeezing every possible reaction from the precious uranium. It was elegant, efficient, and completely unproven for space applications. The real challenge came with heat transfer. Nuclear fission generates tremendous thermal energy. SNAP-2's core would operate at temperatures exceeding 1,000 degrees Fahrenheit. That heat had to be captured, transported, and converted into electricity. The engineering team chose liquid sodium-potassium alloy, known by its chemical symbol, Na-K, as the coolant. This metallic liquid could absorb enormous amounts of heat and flow through the reactor's veins, carrying thermal energy away from the core. But Na-K came with a terrifying downside. It's extraordinarily reactive, exploding on contact with water and burning fiercely in air. Working with NOC meant developing entirely new sealing technologies, new testing protocols, new safety procedures. A single leak during testing could mean catastrophic failure and potentially fatal consequences for the engineers nearby. The team persevered, driven by the knowledge that they were building something unprecedented. The Na-K coolant flowed through primary loops, absorbing heat from the reactor core and carrying it to the conversion system. And here's where SNAP-2 became truly revolutionary. Instead of using turbines or generators with their moving parts and inevitable mechanical failures, the system employed thermoelectric modules. These solid-state devices converted heat directly into electricity through the Seebeck effect. When one side of certain materials is hot and the other cold, electrons flow, creating electrical current. No spinning parts, no wearing components. Just temperature differential and physics. The entire reactor and conversion system massed approximately 950 kilograms, heavy by modern standards but remarkably light for a nuclear power plant, capable of generating kilowatts for years. Every component had been scrutinized, optimized, and tested to the breaking point. The engineers had created something that existed at the bleeding edge of what physics and materials science would allow. But building a nuclear reactor for space meant solving a problem that terrestrial power plants never faced: radiation shielding in a mass-constrained environment. The reactor core emitted intense neutron radiation and gamma rays, enough to destroy unshielded electronics in minutes and deliver lethal doses to humans in hours. On Earth, you solve this problem with mass, thick concrete walls, water pools, distance. In space, every kilogram is precious, bought with rocket fuel and engineering compromises. The SNAP-2 team needed a shield that could protect spacecraft systems and potential crew without making the entire package too heavy to launch. The solution came in the form of lithium hydride, a remarkable material that seemed almost designed for this exact purpose. The hydrogen atoms in lithium hydride are extraordinarily effective at slowing down fast neutrons through successive collisions, like trying to stop a bullet by shooting ping-pong balls at it, except the ping-pong balls actually work because of quantum mechanics. Once the neutrons are slowed, the lithium atoms capture them, removing them from the radiation field. And crucially, lithium hydride is remarkably lightweight compared to traditional shielding materials like lead or tungsten. The shield design itself was ingenious in its simplicity: a truncated cone positioned between the reactor and the spacecraft above it. This shadow shield concept meant only protecting what sat in the shadow of the reactor, allowing radiation to escape harmlessly into space below. The geometry was carefully calculated: too small, and the spacecraft would be exposed to dangerous radiation levels; too large, and the mass penalty would be prohibitive. The final design struck a delicate balance, providing adequate protection while keeping the total system within launch constraints. But lithium hydride brought its own challenges. The material is hygroscopic. meaning it absorbs moisture from the air like a sponge. Any water contamination could compromise the shield's effectiveness, creating gaps in protection that would only become apparent during operation. The engineers developed hermetic sealing systems, encasing the lithium hydride in impermeable containers that could withstand the thermal cycling and mechanical stresses of launch and space operation. Every seal, every joint became a potential failure point that had to be tested and validated. Harold Finger found himself fighting a new kind of battle, not against physics, but against politics. In classified briefings with NASA administrators and Air Force generals, he had to walk an impossible tightrope, acknowledge the genuine dangers of nuclear power in space, but demonstrate that the engineering solutions were sound, show confidence without appearing reckless, admit uncertainties without undermining the program. His credibility and the entire future of nuclear power in space hung on these presentations. The ultimate test came in the early 1960s, when SNAP-2 moved from design to reality. Years of work, over $100 million in funding, approximately $900 million in today's money, countless sleepless nights and solved crises, all converged on a series of ground tests that would determine whether the reactor could deliver on its promises. The reactor achieved criticality smoothly, with control rods providing precise power regulation. Watching the instrumentation as the neutron flux climbed, the engineers saw their calculations transform into reality. The thermal systems performed flawlessly. NAK, coolant circulated at design temperatures. Heat rejection systems maintained proper temperature gradients across the thermoelectric modules. And then came the moment that validated everything. The thermoelectric modules generated 5 kilowatts of electrical power. 5 kilowatts sustained, steady, reliable. Enough to run a small household, or, more importantly, enough to power sophisticated spacecraft systems for years in deep space. Extended duration testing pushed the reactor through simulated multi-year mission profiles. The reactor operated for thousands of hours in vacuum chambers that mimicked the space environment. No air for convection cooling, only thermal radiation to shed waste heat. Every test brought new data, new confidence, new validation that SNAP-2 was ready. The engineers had done it. They had built a nuclear reactor that could power humanity's expansion into deep space. But success became a prison. The moment SNAP-2 proved it worked, something unexpected happened. Security classifications tightened dramatically. The Atomic Energy Commission and Department of Defense began classifying virtually every technical detail: reactor specifications, fuel composition, conversion efficiency, test results, even photographs of the facility. The entire design file disappeared behind classification walls. NASA engineers who might integrate SNAP-2 into actual missions couldn't access the data they needed. Test videos that could have demonstrated the technology's viability to mission planners were locked away. Failure analysis that could have improved future designs became inaccessible. Fuel specifications, thermoelectric converter data, operational parameters, all classified. The paranoid logic of the Cold War had created an absurd situation. SNAP-2 was too successful to share. The very capabilities that made it valuable for American space missions also made it sensitive information that couldn't be released. The reactor that was supposed to power America's expansion into space instead became a secret that couldn't be told, a solution that couldn't be implemented, a masterpiece that couldn't be displayed. Harold Finger sat in increasingly tense meetings at AEC headquarters in 1965 and 1966, watching his life's work being slowly suffocated. The antagonistic forces were no longer technical. They were political, bureaucratic, and economic. Mission requirements were shifting. The rapid evolution of solar panel technology, while still inadequate for deep space, was improving faster than anyone had predicted. More advanced nuclear designs were being proposed, including derivatives of SNAP-8 that promised higher power output. And crucially, the specific missions that SNAP-2 had been designed to power were being canceled or redesigned. The tragic irony was complete. SNAP-2 had demonstrated that the technology was viable. The reactor worked. It generated its target power output. It operated reliably under simulated space conditions. But by the time it was ready, the world had moved on. more advanced systems were available, mission planners were designing around different power requirements, and the classified nature of SNAP-2's success meant that the broader space community couldn't learn from it, couldn't build on it, couldn't integrate its lessons into future designs. The engineers who had devoted years of their lives to SNAP-2 watched their creation become obsolete, not through failure, but through bureaucratic entropy. The reactor that was supposed to fly to Jupiter, to Saturn, to the outer darkness of the solar system, never left Earth. It sat in its test facility, a fully functional nuclear power plant designed for space, going nowhere. Eventually, the program was terminated. The hardware was either dismantled or disappeared into storage. The documentation remained classified. The knowledge, hard-won through years of engineering challenges, scattered as the team moved on to other projects. Looking back across the decades, SNAP-2 stands as a monument to both human ingenuity and institutional dysfunction. The engineers solved problems that had never been solved before. They created materials science innovations, developed new testing protocols, pushed the boundaries of nuclear engineering and space systems integration. The heterogeneous uranium-zirconium hydride fuel design, the NAK cooling system, the thermoelectric conversion modules, the lithium hydride shadow shield, each represented a triumph of engineering over seemingly impossible constraints. The reactor's 5 kilowatt output might seem modest by modern standards, but in 1960, it represented a revolution. 5 kilowatts sustained for years in the vacuum of space from a package massing less than a ton. That power density, that reliability, that longevity, these were the keys to deep space exploration. With SNAP-2, missions to the outer solar system would have been powered by American nuclear technology, carrying instruments that could operate for decades rather than months. But the story of SNAP-2 is ultimately about more than engineering specifications and power outputs. It's about the humans who built it, engineers like Harold Finger, who fought bureaucratic battles to keep the program alive, the unnamed team members at Atomics International who solved the NAK coolant challenges, who designed the shield geometry, who tested and refined the thermoelectric modules. These were people who believed they were building the future, who saw their work as opening the cosmos to human exploration. The secrecy that killed SNAP-2 was born from legitimate concerns. Nuclear technology was sensitive, and the Cold War made every advantage precious. But that secrecy also prevented the cross-pollination of ideas, the sharing of lessons learned, the building of institutional knowledge that drives technological progress. When SNAP-2's design files were classified, when its test results were locked away, when its engineers couldn't publish or share their work, the entire space community lost access to a wealth of knowledge. Future reactor designs had to rediscover solutions that SNAP-2 had already found. Problems that had been solved had to be solved again, wasting time and resources. The 950-kilogram reactor that generated 5 kilowatts of power sits now only in declassified documents and fading memories. The hardware is gone. The facilities have been repurposed or demolished. The engineers have retired or passed away. But the ghost of SNAP-2 haunts every discussion of nuclear power in space. When modern mission planners consider nuclear reactors for Mars bases or deep space probes, they are walking paths that SNAP-2's engineers blazed decades ago. When new reactor designs use uranium hydride fuels, or thermoelectric conversion, or shadow shielding, they are rediscovering solutions that SNAP-2 proved viable in 1960. There's a particular poignancy and success that goes unrecognized. SNAP-2 worked. It achieved its design goals. It demonstrated that nuclear power in space was not just possible, but practical. And then it disappeared, not into the cosmos it was built to explore, but into the classified archives of Cold War secrecy. The reactor that was supposed to power humanity's expansion into deep space instead became a footnote, a might have been, a road not taken. We can only speculate about the alternate history where SNAP-2 flew. Perhaps missions to Jupiter would have launched a decade earlier, powered by reliable nuclear reactors instead of waiting for radioisotope thermoelectric generators. Perhaps the lessons learned from operational space reactors would have accelerated the development of more advanced systems. Perhaps the public would have become more comfortable with nuclear power in space. seeing it as a tool for exploration rather than a threat. Or perhaps the same forces that killed SNAP-2 on the ground would have found other ways to prevent its deployment. What we know for certain is that the engineers who built SNAP-2 achieved something remarkable. In an era when space exploration was in its infancy, when the basic principles of operating in vacuum were still being discovered, they designed and built a nuclear reactor capable of operating for years in the harshest environment imaginable. They solved the heat transfer problem with liquid metal coolants. They converted that heat to electricity with solid-state thermoelectric modules. They shielded the radiation with innovative materials and geometry. They tested their creation through thousands of hours of operation, validating every design decision. And then they watched it die, not with a bang, but with a whimper, strangled by classification and obsolescence. The reactor that could have changed everything instead changed nothing, leaving only the bitter knowledge that it worked, that it was ready, that it could have flown. In the end, SNAP-2's legacy is a warning as much as an inspiration. It reminds us that technological success is necessary, but not sufficient. That secrecy can protect advantages, but also prevent progress. That timing matters as much as capability. That the path from laboratory to deployment is treacherous, filled with obstacles that have nothing to do with engineering and everything to do with politics, bureaucracy, and the chaotic evolution of priorities. The 5 kilowatts that SNAP-2 generated in its test facility represented more than electrical power. They represented human ambition, the drive to push beyond our limitations, the refusal to accept that deep space must remain forever dark and silent. Those kilowatts proved that we could build machines to carry our presence into the cosmos, to power our instruments and our dreams across the vast distances between worlds. That the reactor never flew doesn't diminish what its engineers achieved. They built something that worked, something that was ready, something that could have opened the outer solar system to exploration decades before it actually happened. The fact that institutional forces prevented that deployment is a tragedy. But it doesn't erase the triumph of the engineering itself. SNAP-2 remains a ghost in the machine of space exploration, present in every modern space reactor design, in every discussion of nuclear power beyond Earth, in every mission that ventures into the darkness where sunlight fails. The engineers who built it proved it could be done. They showed us the way, even if we didn't follow their path. And somewhere in declassified archives, the specifications and test results wait. A testament to what was achieved and what might have been. A reminder that sometimes the greatest barrier to reaching the stars isn't the physics of the cosmos, but the politics of Earth. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.